Hello everybody, my name is Jack and I have just finished the Nupoc application process. I interviewed in DC last week and was accepted into the program as a submarine officer. In this video, I'm going to go through the mathematics section of the study guide and explain how I approach and solve the questions. There are going to be 52 total questions in this section, and so I've left the links in the description so that you can jump to any question you're having trouble with. There aren't that many resources out there in accordance with the study guide, so I hope that this video can be of some use. Okay, let's jump into the first question. So this first question deals with complex numbers. Since it's a multiple choice question, the easiest way to do it is probably just to plug in the numbers, but we're going to treat it like a free response question. Our first step here is just going to be to expand out the exponent. So we're going to get y squared plus 1 and minus 2y from there. A lot of this simplification process that I go through in this question isn't really necessary. At any point, you could probably use inspection, especially with the answers given, but I go through the process of dividing out the y's to simplify the terms a little bit because we had a y in every term except for the 1. Then I decided to multiply the y by y over y so I could put the fraction together, and then I have y squared plus 1 over y. And then I also have negative 2 plus 2x, and since the whole entire thing is going to equal 0, we know that the numerator of y squared plus 1 is going to equal 0, and we know that negative 2 plus 2x is going to equal 0. So y squared plus 1 equals 0, y squared equals negative 1, and so y is going to equal the square root of negative 1, which is, of course, I. And on the second little equation there, we're going to have 2x minus 2 equals 0, 2x equals 2, x equals 1. So that's going to be our answer there, and that is answer choice B. So this next question here is just a quick review of ellipses, hyperbolas, parabolas, and circles. By definition, the answer is just going to be a hyperbola. A hyperbola is the set of all the points in a plane where the difference in their distances from two fixed points, the foci, is just a positive constant, but I thought it would be important to go through all the shapes given because they're all pretty common shapes, and hyperbola is probably the least useful and the least common, especially for these interviews. This is the only question I saw that even referenced a hyperbola, while all the other three shapes are very common. So at the top there, we just have the equation for an ellipse, where a is going to be the distance in the x direction, b is going to be the distance in the y. Under that, of course, we have the classic circle. All of this is centered around 0. You'd have x minus h squared or y minus k squared to get the center of the circle or the ellipse. Then under that, we've just got our basic parabola. And then, of course, on the top right, we're going to have our hyperbola, which is going to be the answer to this question specifically. And I think I draw the two foci in there. So next up, I'd just like to quickly go over how you would derive this formula. This is not how I would answer the problem. I think you should just go off knowing the basic definitions of each shape, but it's definitely possible. So if we just draw a hyperbola here, labeling one F2, labeling one F1, hindsight probably should have made that one F1, especially after the steps we'll go over in a little bit, right? So those foci are going to be some positive distance c and some negative distance c away from each other due to symmetry, and we are going to be putting in some random point, and what we're going to say is that the distance is going to be some positive constant, right? That's what we're kind of looking for here. So if we set up a distance formula under that assumption of the distance from the point to actually foci 2 minus the distance from the point and foci 1, we set that up a little backwards, but that's okay. That's going to equal 2 times a, right? 2 times some positive constant. Yep, so if we continue along this trajectory, it just turns into a simplification problem where we're going to have our distance formula, so square root of x minus c squared plus y squared, right, for distance, and x plus c squared plus y squared for distance again, and that's still going to equal our 2a. And now the question is really, how do we simplify this? It's a whole hassle. I just used a computer after squaring both sides. It made it a lot easier. If you want to go through simplifying this expression, you're all good on doing that, all welcome to do that. I don't advise it, but you definitely can. after a lot of simplification, you'll get x squared over a squared minus y squared over c squared minus a squared, which is going to equal 1. If we just let c squared minus a squared equal b squared, we have our formula for a hyperbola. So that's the general structure for how to derive this answer, but I would definitely advise just knowing the definitions of the shapes and going from there. Much easier than this derivation. So this question's a substitution question, and it also just makes sure that you know how distance, velocity, and time all relate. We've got a plane and a jet, both going the same distance, different times, different speeds. One way to solve this that I didn't do here was that since acceleration is 0, we know that the time of the jet plus 10 is going to be equal to 3 times the time of the jet. But instead, we'll just use, since velocity is equal to distance over time, distance is going to be equal to velocity times time. Since they're both going 3,000 miles, we know that the velocity of the plane times the time of the plane is going to be equal to the velocity of the jet times the time of the jet. And we're given the velocity of the plane and the time of the plane both in terms of velocity of the jet and time of the jet. So as we see here, we could be relating velocity times time in jet is equal to 1/3 vt plus 10/3 v. Now we have vt and 1/3 vt on opposite sides of the equation, so we could just minus the 1/3, giving us 2/3 vt equal to 10/3 v. V on both sides, we can divide both sides by v. We get 2/3 t equals 10/3 t. We can both cross out those 3's, and we'll get t equals to 5 hours. Now we could simply do velocity equals to change in distance over change in time, and we'll be doing this for the jet. We're given that the change in distance is 3,000 miles, and we just found that the time is 5 hours, so that's going to give us a velocity of 600 miles per hour. So this question here is just recognizing how to put the equation given into the form of x minus h squared plus y minus k squared equals r squared, which is just the equation of a circle not centered around 0. One way to do this is just to put the x and y terms together. That's going to give us x squared minus 2x plus y squared minus 4y equals 17. Our next step is to do complete the square. So we're going to be taking negative 2 over 2 squared, which is going to be equal to 1. So we got to add 1 to the other side. And negative 4 over 2 squared, which is going to equal 4. So we got to add 4 to the other side. And we're going to be putting that term inside of the parentheses into our new squared term. So x minus 1 squared, because negative 2 over 2 equals negative 1, plus y minus 2 squared, because negative 4 over 2 equals negative 2. It's going to equal 17 plus our 1 plus our 4. So as we could see, we have the equation that we were looking for. So h right there is going to be equal to 1. K is going to be equal to 2, so we have a circle centered at 1, 2. It's not asking for the radius, but it's pretty easy to find from the formula, and that's just going to be the square root of 22. So this question is just working with exponents and a little bit of problem-solving skills as well. What we're trying to do is take these terms that are raised to the 4th and just take the whole expression and make it only second order. So the first thought I had when solving this problem is not how you're supposed to be doing it, which is just that a to the 4th is a squared, and b to the 4th is b squared. We're all done. But obviously, we're going to try and do a little bit more work to get things not in second order like this. This isn't really second order. So one of the first things that we could notice is that a squared plus b squared, a to the 4th plus b to the 4th, we could easily make a substitution for a squared and b squared. When we do that, the situation looks a lot nicer now. And with c squared plus d squared, we almost have c plus d squared. And if we had c plus d squared, we'd just be able to cancel out the exponent with the c plus d down there, and we'd wind up with c plus d. So as we can see up here, if we had c plus d squared, it's almost that, but we have that plus 2cd on the end there. So we can use c plus d squared, but we're going to have to minus a 2cd off the other side so that the equation stays the same. But now we could just split this fraction up. So now we do have the c plus d squared that we were looking for, and luckily for us, minus 2cd only contains a squares and b squares, nothing to the 4th, nothing to the 6th, nothing above second order. So when we rewrite this equation and resubstitute in for a squared and b squared, everything should be second order, which is exactly what we were looking for. So that's how I approach this problem. I'm sure there's other ways to get here, but this is a good one. So next up here, we have another complex numbers question where we're trying to simplify a complex number over another complex number. What we're going to do is multiply by the complex conjugate, and we're going to specifically multiply by the complex conjugate of the denominator because we want a real number in the denominator, right? So we're going to multiply this expression out. We're going to get a real number plus an imaginary number in the top and a real number in the bottom. I squared is -1, so this is going to come out to 9 plus 6i plus 6i minus 4, right? That's going to be all over 9 minus 6i plus 6i minus 4i squared, which is going to go to plus 4i, right? -1 times -1 is +1. Those -6i and +6i terms are going to cancel out, which is why we multiplied by the complex conjugate of the denominator. That's really what we're looking for, and this is going to give us 5/13 plus 12/13i, which is an a plus bi form and is our answer. The next question we got here is a linear algebra question. We can use elimination to solve this without putting things in matrix form, but it's much easier using matrices. So the first way we're going to do this is elimination, and the second way is a method that uses the determinant of the matrix. So we're going to add 5 of that third row, -5 of that third row to the top one. We're going to add +3 of that third row to the second one, and that's going to eliminate the first term in 2 of the 3 rows. And then we're going to pop that third term to the top because that's the form we always want things in. Reduced row echelon form is what we're looking for. We know this has solutions. So the next thing we're going to do, we could see we have a -4 and a 4 in those middle 2 rows. So we're just going to add that second row to the third row, which is going to cancel out the -4 of the third row. So we'll go ahead and do that. It's important to remember not to forget to add the augmented part of the matrix. So a lot of times I might forget to add that 0, 6, 6 section. So when we have a -30 and a 24, we add the 24 to the -30, giving us -6. As we could see, we have -6, -6, and you got to remember what each of those values mean. That -6 is just representative of the z term. And so we know that z equals 1 because on the right we have what's after the equal sign, and on the left we have the variables. So the top row currently is saying that x plus 4z equals 6. So you don't have to do any more row reduction. You could just plug stuff in there because you know that x plus 4z is equal to x plus 4. So we know that x is going to be 2. And similarly, in that middle row, we have 4y plus 12z equals 24. So we know 4y is going to be equal to 12, y is equal to 3. But I go through the matrix row reduction just because it's good practice anyway, and you might as well do it just to be sure. The only way really to be sure, of course, is to plug everything back into the top equation. But 1, 2, and 3 definitely looks like an answer that you should be getting. So I'm going to let this matrix multiplication run out, and then we'll jump into the second method. Okay, so on to method 2. So in this method, we're going to be taking the determinant of the matrix we were using up there, and then we're going to be finding 3 separate determinants by putting that augmented aspect inside. So let's just start with A equal to our matrix at the top. So the way you find the determinant of a 3D matrix is that you're going to take those top 3 terms of 5, -4, 2, and multiply them by the matrix that's left, the 2 by 2 matrix, when you cross out the row and column associated with that term. So when you're doing 5, you cross out 5, -4, 2, 5, -3, 1, and you take the determinant of that 4, 0, 0, 4 matrix. And finding the determinant of 2 by 2 matrices, that's an easy set formula to use, while there isn't that easy set formula for a 3 by 3. So the determinant of 4, 0, 0, 4 is going to be 16 minus 0, which is, of course, 16. The determinant of -3, 4, 0, 1 is going to be -12 minus 0. And I think I'm going to illustrate a little more specifically how to find the determinant of negative 3, 4, 1, 0. The way you just got to do it is you multiply that top left term by the bottom right term and minus it by the multiplication between the top right and bottom left. So negative 3 times 0 minus 4 times 1 is going to give us negative 4. So now we're just going to subtract 48 and 8 from 80 to get the determinant of the matrix there, which is going to be 24. Next, we're going to find the matrix for the determinant of x, the determinant of y, the determinant of z, and what those matrices are just the matrix A that we have, except we're going to take 0, 6, 6 and put it in the x column, the y column, and the z column. 0, 6, 6, where that's coming from is that's the answer, not the answer, but what our original equation equaled. So originally we had 5x minus 4y plus 2z equals 0, so that's the 0. So dx is the determinant of the matrix 0, 6, 6, and then just the regular matrix we had before. dy is the same thing, but 0, 6, 6 in the middle row, and dz is going to be 0, 6, 6 in the final row, where those z terms are. And just to add a quick mistake, the final row in the z term is 0, 0, 6. It should say 0, 6, 6, and in my head I think I'm reading 6, so it doesn't mess up any of the math, but it would have if that was a 0, but it's going to act like a 6 in the math, so just pretend like that's a 6 there. The rest of this is just going to be taking the determinant of the 3D matrices and then putting it over 24, because if you look at x equals dx over d, y equals dy over d, z equals dz over d, it's the same process 3 times, so with 0, 6, 6 in different columns. If you know how to do the determinant of 3D matrices, you could just skip over this part with no consequence. If you don't, though, these are great matrices to practice with. So I think now I'm just going to let the determinants just run out as we find them. Yeah, so as we could see there, we have 4 times a negative 24. Of course, if that was a 0 instead of a 6, we'd actually have a negative 18 there, because it'd be negative 3 times 6 minus 0 times 1, which is negative 18, but it's actually negative 3 times 6 minus 6 times 1, which is negative 24. So we just wind up getting 48 over 24, which is 2, which is our x, 72 over 24, which is 3 for our y, and 24 over 24, which is going to give us a z of 1. So these are 2 different ways of solving a system of equations. Of course, you don't need matrices, but they definitely make things simpler. And if not simpler, they definitely make them neater. So here we're just going to do a quick overview of logs, especially the natural log. We're going to use logs in the natural log later, but this question asks for it, so we'll talk about it. So the natural log is a log with a base of e. E is just a number. It's about 2.72. So you graph that, you just get a straight line, of course, of the base in the natural log. So there are also a lot of properties of logs which are pretty cool. For example, the log of x y is equal to log x plus log y. Similarly, log x over y is equal to log x minus log y. Here we could see the natural log of e squared equals 2, because e squared equals e squared, because the base is e. So the natural log of e to something is going to be equal to whatever that something is. That's a property we use a lot. Another fascinating aspect about e to the x is that its derivative is itself, and its integral is itself as well. We'll go into more complicated functions like this later on. E to the I theta also by definition is cos theta plus I sine theta. You might have seen the famous expression e to the I pi plus 1 equals 0. This is one way of understanding it from e to the I theta. So we're going to have cos pi plus I sine of pi. Sine of pi is 0. Cos of pi is negative 1, so we get 0. One last thing we could do is graph the exponential function. Calling it an exponential function is a bit of a hint in the sense that Of course, it's going to grow exponentially. E to the x is never going to be negative because it's going to approach 0 as we get to huge numbers, and it's going to approach, well, it's going to approach 0 as we get to huge negative numbers, and it's going to approach infinity as we get to huge positive numbers. Next up, we got a real quick question, just making sure that we know the circumference formula for a circle and the area formula for a circle. We got a circle that has an area equal to its circumference, so pi r squared is going to be equal to 2 pi r. We can cancel out that pi, cancel out one of the r's, and just get r equal to 2. So now we're going to be deriving the equation for a circle. So let's set up a circle. We're not going to center it around the origin. So we're going to have some point xy and some point hk. We're going to draw our circle. Now we're going to draw a line. So we're going to need to use the distance formula to find the distance of that line. It's going to be equal to the square root of h minus k squared plus y minus k squared. If we square both sides, we're going to get d squared equal to x minus h squared plus y minus k squared. And of course, this is basically the formula for a circle, but we just got to clarify that d is in fact our r. It's going from the center to the outer ring. So we got our formula now. So in this next question, we're given a closed box, we're given what the length, width, and height are in terms of height, and we're tasked with finding the surface area given a surface area equation. So this question is basically just some algebra. We're just going to be equating the two surface area formulas and solving for h. Once we find h, we'll have both the length and the width, and our goal is just to find the dimensions of the box. So we're setting up right here the surface area equation given, 10, 2 times h minus 10 times h, and on the right, we're given the surface area equation of the box in terms of 2 times the length times the width plus 2 times the length times the height plus 2 times the width times the height. We've got an extra 8 in in every term, so we can cancel out that h. We also had a 2 in front of all those terms, so we cancel those out and put in a 5, leaving us with 5 times 2h, which is 10h, 5 times negative 10 for negative 50, and then we could just have what's left on the right side. This question isn't all that tricky as long as you know the surface area equation, which is up there in the top middle. After that, it's just plugging in the given values and solving. So I'll let this run out if you didn't know how to get to the end here. So in this next question, we're going to be deriving the quadratic equation, which comes in handy anytime you have a constant times x squared plus a constant times x plus another constant equal to 0. You should probably have the quadratic equation in mind if you were planning on trying this first without seeing how it's done. Obviously, eventually we're going to have an x equal to something, so we're going to want to get that a away from the x, so it seems smart to divide that a out from the x term, right? So now we've got x squared plus b over a times x equal to negative c over a. And our next step is going to be completing the square. Hopefully, we all know how to complete the square, right? We're going to have b over 2a plus x all squared. And then we're going to have to put b squared over 4a squared on the other side so that the equation stays the same as what it was. So that all looks good. Now we're going to rewrite the expression with the minus c over a on the other side. And we know in the quadratic equation we have b squared minus 4ac. So we could put that whole fraction together by multiplying c by 4a. So now we have the 4ac we're looking for, but we have 4a squared on the bottom, right, instead of 2a. But that'll work itself out because we're going to take the square root of both sides, taking x plus b over 2a squared, just making it x plus b over 2a. And then the other side, we're going to have the square root of b squared minus 4ac. We know everything should be all over 2a, and where that comes from is that 4ac is, when you put that in the square root, you could pull out the 4 because the square root of 4 is 2, and you could pull out a squared because the square root of a squared is a, and you'll just get everything over 2a there. Final step, just minus that b over 2a to the other side, and you'll have x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And it's plus or minus just because we took the square root there, right? So it could be plus or minus what's inside the square root. So this next question here isn't really a derivation question. I think the idea that they're getting at is just that you know some general properties of spheres against cubes, against tetrahedrons and stuff like that. In the answer key that they'll provide you there, they don't go through any complicated derivation of this fact, but I think it's just important to know that since a sphere is going to be perfectly symmetrical, infinite sides, its surface area is going to be the smallest for the volume that's enclosed inside of it. And when you go to things that have the least number of sides, right, cubes and tetrahedrons, the opposite fact is going to be true. So just plug in some numbers, try and remember this, it might come in handy. So this next question can be solved in a bunch of ways. I go through two and show that three are pretty reasonable, but we're just trying to find any curve that goes through the points 0, 4, 2, 0, and negative 2, 0. So the first one that I thought of was a parabola, just one that's upside down, right? And so it's going to go through negative 2 and 2. Those are going to be its two zeros, and it's just going to have a y-intercept of 4. So the equation that's going to relate to that curve is just going to be y equals negative x squared plus 4. The next idea is an ellipse, which you could come up with pretty easily, and by looking at the parabola, it's really easy to see because you're just kind of taking that parabolic curve and connecting it at the bottom, right? Just drawing a little U. So the formula for an ellipse, equation for an ellipse is x squared over a squared plus y squared over b squared equal to 1. So for coming up with the equation, you basically just got to figure out what a and b are, right? In this case, a is going to be 2 and b is going to be 4. And so a squared is 4 and b squared is going to be 16. This ellipse is not drawn to scale, of course, as our distance to negative 2 is about 5 times the distance to 2. And the final way, I didn't go through finding an equation. I mean, they only ask for one. A parabola or an ellipse are definitely the simplest, but some sort of cosine wave also works here because we have symmetry on both sides. And if you could just think of any cosine wave with an amplitude of 4 that goes through those points, that should be good. So this next question here is a pretty important one. We're going to be deriving the area formulas for the triangle and the circle and the volume for the pyramid and the cone. This is a question that they love asking. Questions similar to these, not always these shapes, but derivation of formulas like this geometrically are pretty important. So we're going to start with the triangle. We're going to draw a line there centered, not centered, but with a y-intercept at 0. It's going to have a rise of h, a run of the base, right, height and base. So we're going to have a line equal to y equal to h over b x, right? H over b is the slope. So we're going to then integrate to find the area under that curve from 0 to b. That should give us the area of our triangle, right? So we could pull the h over b out of the integral because those are just constants, the height and the base of the function. The integral of x dx is x squared over 2, right? And then we're going to add the bounds of integration, 0 to the base. You could also do this the other way, but you'd have to make the slope negative, and you need some sort of y-intercept. That y-intercept would be the height of the function then, right? So we wind up getting b squared over 2 minus 0 squared over 2, which is just going to be b squared over 2. We can cancel out those b's, and we'll get 1/2 base times height. Okay, so let's move on now to the area of the circle. There are two ways in which I go about doing this. The first uses a double integral, and the second uses a single integral with the equation for a circle. So when we're doing a double integral in polar like this, we're going to be going from, for how many degrees we're doing, since it's a circle, it's going to be 2 pi degrees, right, 360 degrees, because we're rotating all the way around. The radii is just going to be 0 and r, right, because we only have one radius, and what this double integral is basically doing is taking a radius, whatever radius that's going to be, and integrating it around in a circle. That's basically what a circle is, right? It could just be a radius circled around because it's symmetrical, right? So we're going to be doing 0 to 2 pi, 0 to r dr d theta. So first we're going to look at that first integral that goes from 0 to r dr. That will give us r squared over 2 d theta. Then we have an integral that has r squared over 2 and d theta, right? So we could pull the r squared over 2 out. We got an integral of d theta. It's going to give us theta from 0 to 2. Now we could just plug in 2 pi and 0 to give us r squared 2 pi over 2, which gives us pi r squared. A lot of times in integrals, I'll skip plugging in a 0 if it's just going to be 0 over something, right? The only time you really want to make sure you're plugging in zeros in is when we have constants, right? So that you don't actually plug a 0 into that, or whenever you have cos or sine waves, also the 0 is going to be important, right? Because cos of 0 is 1. Next, we're going to use the equation for a circle, which is x squared plus y squared equals r squared. Rearrange the terms to get it in terms of y. Now, the next thing we're going to do is a little bit more complicated, and it's just going to be converting into polar coordinates here. So x is going to be r sine theta, y would be r cos theta, but we don't have to substitute in for y, right, because we're going to be integrating that function there. So we're going to integrate r squared minus x squared dx. dx is the derivative of r sine theta, which is r cos theta, right? R is just the radius; it's a constant in a circle. And so now we're gonna sub in. So we're gonna get sine squared there, r squared there, because that's what x squared is going to be, and then dx is going to be r cos theta. Now we're going to want to pull the things out of that square root sign, right? So we can integrate a little better. We're also going to need to put the bounds of integration in now. So you can integrate to 2 pi, but it's much easier to just integrate that one function in just the first quadrant, right? So we're going to integrate from 0 to pi over 2, and we're going to multiply by 4, because this integral is going to give us the area in that top right quadrant. Not drawn to scale, once again. Obviously, the top right quadrant is not any bigger than the other ones because we're centering this circle around 0. Right, so we got r squared minus r squared sine theta, and we could pull out an r squared, right? Because we've got an r squared in both terms. The square root of r squared is r, right? So this is going to be r times 1 minus sine squared theta, and 1 minus sine squared theta is cos squared theta, right? Because sine squared plus cos squared is equal to 1. So this term, the stuff inside of the square root, is going to turn into r cos theta. So now we have 4. And then the integral from 0 to pi over 2 of r cos theta times dx, which actually is also r cos theta, right? And we're integrating with respect to theta, so we're going to have d theta here. So we could pull out the r squared, but we can't pull out the cos squared. Next thing we're going to do is show what cos squared is. There's a trig identity here that cos squared equals 1/2 plus cos 2 theta. I'm going to show why, right? When you multiply cos theta by another cos theta, right, it's equal to cos of that first theta plus the second theta plus the cos of that first theta minus the second theta all over 2, right? And since our thetas are each 1, they're each the same, right? Cos theta minus theta, that's cos of 0, which is 1, and then we're going to have cos of 2 theta. So that's one way to arrive at that trig identity if you didn't know that and you were having trouble with the cos squared theta there. So now we've got a much easier integral to integrate, right? The integral of 1/2 d theta is just 1/2 theta, right? So we're going to get that. I think I split the integral up first here, right, into 1/2 plus the integral of cos 2 theta. All of this is over 2. And so now we'll just integrate and plug the bounds of integration in, right? 1/2 theta, pi over 2 times 1/2 is pi over 4. And you don't have to bother with the 0 there because it's just going to be 0 times 1/2, which is 0. We could do a u substitution. Anytime you have cos of 2 theta like that, though, you know that u is going to be equal to 2 theta. Du is 2, right? So we're going to go times 1 over 2 du. That's going to give us 1/4 times sine of u, or 1/4 times sine of 2 theta. So now we've got that first integral with the bounds in. We're going to plug the second integral with the bounds in. And we should come out with the area of a circle formula, right, which is just pi r squared. So, yep, things are definitely looking good there. Since we have 2 theta, luckily, well, not luckily, it obviously is going to work out this way, but so we got 2 times pi over 2. 2 pi over 2 is just pi, right? So sine of pi is 0, sine of 0 is 0. That whole sine function is going to go to 0, and we're just going to be left with 4r squared times pi over 4, which is, of course, going to give us our pi r squared. So this is a little bit of a longer way of getting to the same thing. Definitely much simpler to go into polar coordinates, but if they ask for another way or they're asked for something more, this is definitely good to have as a backup. Okay, so now we're going to be going into the area of a pyramid, right? My pyramid skills at drawing are really not very good. But the idea when we're integrating this, I think I do it for both a square-based pyramid and a rectangular-based pyramid, is just that we're going to draw a little circle in for, if you could imagine, the top of that period there, and we're going to integrate that smaller square all the way down to the base, right? So we know that the full height of the pyramid is A, the full base length of the pyramid, the full height of the pyramid is H, the full base is A, and we're going to create a little square that's proportional to the big pyramid that has a length of B and is Y distance from the top. So by equating that, because they're proportional, right, those ratios, we can get B squared in terms of the things we're looking for, right? And so we're just going to integrate that B, that the area of that little box all the way through the height, right? So the reason it's B squared and not B is just because this is a square base pyramid we're looking at first, so the area is going to be B times B, right? So we're going to integrate the area all the way up the Y, and that should give us the volume of the full pyramid, because we're just integrating that cross-sectional area all the way up, right? So now we could plug in what we found for B squared due to that little ratio idea there. We could pull out A squared and H squared because that's just the length and width of the base, and H is just the height of the pyramid, right? So now we've just got Y squared by the power rule is just going to give us Y cubed over 3. And I think we could already see where this is going from 0 to H, right? We're going to plug in that H there. We're going to plug in the 0 there. The 0's not going to do much for us, and we're just going to have H cubed over 3 times A squared over H squared. The H squared is going to cancel out with the H cubed, giving us 1/3 the length squared times the height, right? This is a square base, so A is just representative of the dimensions of the base. Now I'm going to go over the rectangular pyramid next. I think usually a square pyramid is definitely sufficient, and the rectangular pyramid, I use the exact same method, except I just specify that we just do 2 little proportions there, one for the length, one for the width. It's basically the same thing. I think I'll stop talking over it now because I'll just let you follow. This is a pretty reasonable one to skip if you understand the square-based pyramid, or definitely one to try for yourself if you want to make sure that you understood it if you didn't know it before. So as we could see there, we just did 2 separate proportions for A and C, which represents the length and the width of the function. It's going to come out to the same thing, except the volume is not just going to be dependent on one base length where we had A squared before. It's now just going to be A times C. But we're still going to just have a Y squared inside of that integral, so it's going to come out the same. Looks like there was a little mistake there. I think I confused which ones I was doing. So I had the proportions in terms of A and in terms of C, but I need them in terms of B and in terms of D, because what we're integrating is that little rectangle, right? We're not integrating the big base, we're integrating that little rectangle all the way. And I try my best to draw it there. It's really not that great of an illustration, but that's the idea, right? We're integrating B times D, the area of that little rectangle, all the way down. Yep, and so as we could see, we get the volume for a rectangular base pyramid, right? A would be the length, C would be the width. They're just the dimensions of the base. Okay, now we're going to move on to the cone. I believe I'm going to do this in two ways, one using the washer method and one using that proportion method that we just went over. The reason you use the proportion method is just because it's not, the radius is not the same over time, right? It's changing, so we got to integrate those proportions up there, right? So we're doing the same thing except the area that we're integrating is not equal to a base. It is not equal to a length times a width. It's going to be equal to pi r squared, right? So we're going to take the proportion of that big radius and that big height, the full height, and then we're going to take one of those little circles and make that a little radius and a little height of y, proportion those up, and we're going to get a little equation for the small radius. And we're going to be integrating that small radius times pi, right? Because area of a circle, pi r squared, we're going to be integrating pi r squared all the way up from 0 to h. And we just found r in terms of the full length of the cone, the full height of the cone, and the full radius of the cone. So we could just plug that in, do the exact same thing. It's a very similar integral as last time, except the constants on the outside are, that's going to be the only difference, right? We're still going to be canceling out that h squared with an h cubed. We're going to get a 1/3 from the integral, and we're just going to have pi r squared in there because we're integrating a different area this time, right? Yep, so there we go. We got the volume for a cone. Now we're going to do method 2, which I think would be definitely a better one to learn because it's more applicable, right? These proportions are not really applicable to much, but the disc and washer method are very useful to learn, right? So we're going to be, instead of, like, this looks very similar to the triangle setup, but instead of just taking the area under the curve, we're going to be rotating that area around the x-axis, right? So we've got the function again, which is going to be the radius over the height, right? If you imagine the cone, that's the height of that function is actually the radius, right? So that's our slope there. This is the disk or the washer method. In the x direction, it's one, in the y direction, it's the other. And what you do is you integrate from a to b of pi times f of x squared, because the radius of your function is changing. F of x is kind of the radius. If you look what it's going to look like over there, it's going to be a cone shape, right? Because we're going to be rotating that around. If you could imagine rotating the function around the x-axis, right? So this is just another way to get the volume of a cone. So now we're going to integrate from 0 to the height, right, because we're doing it in the x-axis, pi times f of x squared, which is r squared over h squared times x squared dx. And now this should look very familiar because we just had this integral in the last question, I believe, except the only difference was that the x was a y because we were just integrating it up instead of over the x-axis, right? So this is going to give us exactly what we're hoping for, pi r squared h cubed over h squared times 3. Cancel those out, and you will get your volume for the cone again. So this is good. We'll practice this more with other functions. So next up, we're going to be finding the area between two curves in two different scenarios. And the idea for this is that when you're not given any bounds of integration, you just want to find where they intersect, find what that area looks like, figure out which function's on the top, which function's on the bottom, and then just set up an integral. It's pretty formulaic like that. So our first two curves are x cubed and x squared. As you could see, there's going to be a small area in there. Oh, that's a little bit too small, right? But we're going to be trying to figure out that area. So we're going to have to figure out, yeah, it looks like I draw it a little better over there, right? Okay, not that much better. I actually think it's the opposite, right? The x squared is going to be on top. But regardless, right, you can draw your function, right? And we're going to get a to b of f of x minus g of x. That's the formula we're going to be using to find the area between two curves, right? But we have to figure out what that a and b are. So where do they intersect? Where are those 2 points, right? So we're going to set x cubed equal to x squared. By inspection, you could probably figure out that this is going to be x equals 0 and x equals 1, right? 1 cubed is equal to 1 squared. 0 cubed is equal to 0 squared, right? So our a and b are going to be equal to 0 and 1. Now, to figure out which one is f of x and which one is g of x, you just have to figure out which one's on top, which one is bigger in that interval you're looking at. So since we're looking from 0 to 1, a great test function is obviously going to be 1/2, right? So the bigger function is going to be f of x, because what we're really doing is we're taking the area under the curve of the bigger function, subtracting the area under the curve of the smaller function, and that will give us the area in between, right? That's the concept. So as we can see, x squared is higher, right? The little drawing I have at the top is actually the opposite of what it's going to be, right? That shows x cubed being higher, but x squared is really going to be higher in these functions, right? X squared is above. Yeah, bad drawing. Glad I clarified there. Okay, good. So I'm gonna do a better drawing there where we have x squared is above x cubed, right? So x cubed is a higher exponent, so it's gonna be lower between 0 and 1, but then it's gonna get higher much faster, right? So that third drawing is really the area between the curves that we're looking at here. So we're gonna have x squared minus x cubed. X squared, the integral of x squared is x cubed over 3. The integral of x cubed is x to the 4th over 4, right? By the power rule. Guess I decided to draw the power rule there. And so that's going to just go to 1/3 minus 1/4 minus 0/3 plus 0/4, right? But we don't really have to plug the zeros in. And that's going to give us 1/3 minus 1/4, which is equal to 1/12. So that's the area between those curves, right? Steps are find where they intersect, find which one's on top, and then just do the integral, right? That's in these kind of questions where you just have two curves. It gets a little more complicated if you're finding the curves bounded by different things, you know, but this is pretty straightforward. So now we have x squared and x, so where are x squared and x equal? Once again, 0 and 1, right? So now we have to figure out which is bigger between 0 and 1, right? Which is on top. And we could tell graphically that that's definitely going to be x, but if you just plug in 1/2, right, 1/2 is going to be bigger than 1/2 squared. 1/2 squared is 1/4, right? So now we're going to set up the integral, which is going to be from 0 to 1, of course, and then it's going to be x minus x squared, because x is the function on top. We're basically, if you could imagine it, taking the area under the curve of x from 0 to 1, and then we're taking the area under the curve of x squared, right? So the difference between those curves is going to be that little area. So x integrated is x squared over 2, x squared integrated, x cubed over 3, 1/2 minus 1/3 is 1/6. So the next one here definitely starts off simple, but there's a little trickery that goes on in finding some area later on. So first we have the function x squared plus x minus 6, and we are going to have to graph that. You could probably tell that this is a parabola, but no harm in going through the process of finding the maximums and minimums and finding the concavity, right? So 2x plus 1 equals 0. That's where we're going to find our max at x equals negative 1/2. And it's going to be a minimum, right? Because we have a parabola. That little bottom is going to be our minimum. Next, we're going to find the zeros of the function. This can be factored. And so we know that the zeros are going to be -3 and 2. So now we can go ahead and draw that function. And the second part of the question is asking for the area between this function, the function y equals -4, and the x-axis. It's a bit of an ugly parabola there, but I think it gets the job done, right? At least until we're going to have to draw the y equals 4. But that's about what our function's going to look like, right? We got our zeros at -3 and 2. And so now I'm illustrating a bit how we're going to try and solve the integral. You can't just set up one integral here. You're going to have to break it into parts. So we have a 3x4 rectangle, as you could see, in the middle, and that is where the y equals -4 function is going to intersect with our function that we have. So we got to figure out that that's a 3x4. So we have x squared plus x minus 6 equals to -4, right? When are those functions equal to each other? They're equal to each other at -2 and at 1, right? So the area under, the area between these functions and the x-axis is just going to be the area under the y equals 4 curve, which is going to be just a rectangle, right? So we could find the area of that rectangle, but that's not the area that we're looking for, right? Because we also need the area of those little slopes on the side, right? The area between the function and 0 at those points. So we have to set up an integral from -3 to -2 of the function, right? And we're going to set up another integral from 1 to 2 of the function again. and then we're going to add 12, right, because that's the area of that big rectangle. But one thing we're going to have to add in here is a negative sign, because we're taking the area under a curve, but everything is under the x-axis, so we're actually finding the area between two curves. The area between two curves that we're finding is between y equals 0 and the function we're having. So it's 0 minus that whole function, right, f of x and g of x. Yes, so whenever you're taking the area under a curve of something that's under the x-axis, you're acting like, when it's bounded by the x-axis, right, as it is in this question, you're going to be doing 0 minus that function. So we're going to have to distribute that negative out. So you have to add those little parentheses, and now it's just solving an integral, right? The hardest part of this question is the setup. So just remember that you're going to have to break this integral into 3 different parts. You're going to find the area between the function and 0 at the 2 points before they intersect with -4. Then the area under -4 is the area that we're looking for. And then we just got to add all 3 of those areas together and we'll get the answer. So I'll just let this integration run out if you need any help with it, but I'm sure that you could do it at this point, and so I'll let that finish up. So as we can see here, it's very important not to forget to add that 12 at the end, right? And we're going to finish up with 49/3. So this question is asking us to find the volume of the function 1 over x rotated around the x-axis. One interesting aspect of the function 1 over x is that it actually has a finite volume and an infinite surface area, which is really interesting. But that's not what this question is really asking about, so we're just going to quickly graph y equals 1 over x, and then we're going to use the disk washer method to find the volume, right? So what that method does is that it is going to be an integral from a to b. In this case, we're given that we're finding it from 1 to infinity of pi times the function squared, right? So we write it down right here. So what's our function? Our function's 1 over x. We have 1 to infinity as our bounds. And so now we're just doing an integral, right? The integral of 1 over x squared is the same as the integral of x to the negative 2. X to the negative 2 plus 1 over negative 2 plus 1 is going to be negative 1 over x. So now we just have pi times negative 1 over infinity plus negative 1 plus 1 over 1, right? So that's just going to give us pi as our final answer for the volume here. Next up, we're going to be finding the area between two circles, except we can't just use the area of a circle formula. We're going to have to use calculus, right? So you got a little taste of this when we were finding the area of the circle formula generally, but now we're going to be plugging in specific radiuses into the bounds, right? So if you just use the area formula, you can come up with the answer very quickly at 3 pi. Jump the gun there a bit. And so now we're going to have to use a double integral to figure this out, right? So we're going to be doing theta 1 to theta 2, r1 to r2 of r, right? And our r1 and r2 are going to be the given radii, which are 1 and 2, and our theta 1 and theta 2 are going to be 0 to 2 pi because we're integrating around the whole thing. I think that's supposed to say with calculus. It seems that I got a little lazy there, but we're going to go r is integrated to r squared over 2. We're going to be doing that from 1 to 2, right? So 4 halves minus 1 half is 3 halves. Now we're integrating 0 to 2 pi of 3 halves d theta. Pull that 3 halves out. We get 3 halves times the integral of d theta, which is just theta, from 0 to 2 pi is 3 times 2 pi minus 3 over 2 times 0. That's 0. That's 6 pi over 2, and we're going to get our 3 pi answer again. Now we've got a pretty long question in which we're just going to be going through a bunch of different integrals, right? It's very important that we know how to integrate, so it's good to get some practice in. So our first integral is x sine x. We're going to be using integration by parts. Whenever you have an integration by parts question like this, it's always important to make sure that your x is u, right? Because when we take the derivative of x, it's going to be 1, so we're going to have an integral that's solvable, an integral that's not in parts. So u is our x, dv is our sine, du is 1, and v is going to be the integral of sine x, which is negative cos x, right? So we have negative x cos x minus the integral of negative cos x times 1, which is going to be negative x cos x plus the integral of cos x, which is going to equal sine x minus x cos x, which is our final answer. And always add c, right? I don't think anyone will nip you for that, but it's an important thing to remember. Okay, let's move on to the second integral where we just have x times x squared minus 4 inside of a square root, right, to the 1/2. Hopefully, we got to recognize that this is a u substitution. U is x squared minus 4, du is 2x. We're going to substitute dx for 1 over du, right? And we're going to have x times u to the 1/2 times 1 over 2x. We'll cancel out the x's so we don't have to bother with integration by parts, simply leaving us with an integral of u to the 1/2. U to the 1/2 is just going to go to u to the 3/2 over 3/2. And when we multiply that by 1/2 and substitute in back for u, we're going to get x squared minus 4 times the square root of x squared minus 4, right? Because something to the 3/2 is the same thing as saying its regular self times the square root, right? That's the same thing. So we got what was just said before, all over 3, right? Because that 3 didn't cancel out, the 2's canceled out. So that's how you do this one, use substitution. Now we'll move on to the third integral, which is e to the x, e to the fourth minus 3 over x squared. This you just got to recognize that you got to break it up into 2 different fractions, right? If you break up the x squared fraction, you're just going to get 2 integrals that are pretty basic. E to the fourth is a constant, 3 is a constant, right? You could just pull those out of the integrals. Now you've just got integrals of x to negative numbers. Use the power rule, and you will be able to figure out this one pretty easy. Yep, so we're going to get negative e to the fourth over x plus 3 over 2x squared. Rearrange that, add a c, and you got the answer to this one. As long as you remember to break up the fraction and break it into 2 integrals, you should be fine there. Here we go on to d, which is the integral of e to the negative x plus 3x squared. That should be a real simple one, right? The integral of e to the x is equal to e to the x. The integral of e to the negative x is equal to 1 over negative 1, right, times e to the negative x. When you take e to the u, it's equal to e to the u. U is going to be equal to negative x, so du is equal to negative 1. So whenever you have e to the x, and as long as x isn't to a certain power, you could just take whatever's in front of the x, do 1 over that, times the function inside the integral, and that will give it to you, right? But u substitution is always safer if you don't want to use that rule. So we're going to get negative e to the negative x, x squared, is going to go to x cubed, so we're going to have 3x cubed over 3, and we're going to just have x cubed there minus e to the negative x. We got the fifth integral of x sine squared x plus x cubed. We could definitely break this up into 2 integrals because integrating x cubed is pretty easy. That's just going to be x to the fourth over 4. And then we're going to have to integrate x sine squared x. How do we do that? Well, integration by parts is always a good idea when you have x times a function. But what is the integral of sine squared x? Well, the way that I like to go about doing it is using trig identities, right? Sine squared x is equal to 1 minus cos squared x. Cos squared x, as we went over before, is equal to 1/2 plus cos of 2x. So we can turn sine squared x into 1/2 minus cos of 2x over 2. And then when we integrate that, we get 1/2 x minus, and using u substitution for 2x minus 1/4 times sine of 2x. So now that we have our expression for the integral of sine squared of x, we can just do integration by parts, right? uv minus v du. U is x, v is what we just found, 1/2 x minus 1/4 sine of 2x, minus the integral of du, which is just 1, right? The derivative of x is 1, and then times v, which is what we found again. Right, sorry, it gets a little small there. We could distribute out that x to get 1/2 x squared minus 1/4 x sine of 2x. And then we could break that integral into 2 parts, right? Distributing that negative is going to give us the integral of 1/2 x plus the integral of 1/4 sine of 2x. If you're recognizing the pattern, that should be sine of 2x, of course, not sine of regular x, but we'll plug that back in some other time. If you're recognizing the pattern with integrating a sine or a cos to 2x, you're just going to take the 1/2 out and take the integral of whatever function you're integrating, right? So 1/4 sine of 2x is going to go to 1/8 sine of u, which is going to give us 1/8 negative cos of u, right? And u is 2x there. So now we got everything. We've integrated both of our integrals there. So we're going to have 1/2 x squared minus 1/4 sine of 2x minus 1/4 x squared plus 1/8 cos of 2x because we have to distribute out that negative sign, right? So our sign's flipped. 1/2 x squared minus 1/4 x squared is 1/4 x squared. So x squared minus x sine of 2x, minus sine of 2x, x all over 4 plus 1/8 cos of 2x is going to be our final answer for the integral. And plus c. And don't forget the x to the 4th over 4, right? Because we had x to the 4th over 4. Don't forget that that other integral we broke off real early there. Okay, so now we're going to move on to our next integral, which is the integral of secant u tan u. Now, obviously, the easiest way to do this integral is to recognize that that is, in fact, the derivative of secant, right? So the integral of secant u tan u must be secant because the derivative of secant is secant tan u, right? So that's definitely a reasonable way to get to the answer, but if you don't recognize that, we will go through how to do that anyway. So secant is equal to 1 over cos, right? And tan is equal to sine over cos. So you can change this integral into 1 over cos u times sine u over cos u. And this will be an easy u substitution, right? Because the derivative of cos is negative sine. So if you make u equal to cos, then the sine will cancel out, right? I use w instead of u substitution because we had u's there already, but it's not really going to make a difference. I actually apparently used u again there. So we're going to have negative 1 over u squared because the derivative of cos is negative sine. Sines cancel out. We got a negative there. Negative 1 over u is equal to 1 over u, which is equal to 1 over cos u. Remember to put those w's in. 1 over cos u is secant u plus c, and that's going to be our answer. So if you didn't remember that the derivative of secant is secant tan, that's another way to go about it with a little bit more problem solving. Our next integral is x e to the x. This is a basic integration by parts one. A little more complicated one would be if we had a sign there instead. Maybe we'll go over that one later, but this is just going to be u is equal to x, dv and v are the same at e to the x, du is 1, x e to the x minus e to the x plus c is going to be our final answer there. Next up, we have h, which is y plus 3 times y plus 1. This integral is basically just asking if you're going to freak out that they changed the x's to y, which I don't think any of you will. As long as you distribute out those two parentheses expressions, you're going to get a pretty simple integral, all just power rule. So I think we could all do this one. Our next one is going to be a triple integral. Now, a triple integral isn't really any more complicated than a single or double integral. They can be more complicated to set up, but to evaluate, not really. Basically, what we're going to do is break it up into 3 integrals. So we're going to do the innermost functions, the innermost integrals to the outermost integrals. So we have d theta, d phi, d theta, dr, right? So we're going to do the d phi integral first. R sine theta, none of that has any phis, so it's just going to be d phi in there. So it's r sine theta phi, and then we're going to plug in the bounds of integration there, right? So we're going to get r sine theta times pi over 2. And I go through plugging in that 0 there. Now, since we just evaluated that innermost integral, we're going to plug what we got back into those next 2 integrals, right? So we still have the integral from 0 to r, the integral from 0 to pi over 2 of pi r sine theta over 2 now, d theta dr. So now we're going to look at that d theta integral from 0 to pi over 2. So as long as you remember to associate that first differential with the first integral and you work from the innermost ones to the outermost ones, it's basically just like solving 3 integrals. Just remember what differential you're in, and you should be good, right? So here we have to remember we're in theta, so we're going to be pulling out anything that doesn't have a theta term, which was just sine theta. So the integral of sine theta is negative cosine of theta, and so integrating that from 0 to pi over 2, cos of pi over 2 is 0, cos of 0 is 1. It's just going to give us pi r over 2. Now we're going to go back to the third and final integral, 0 to r, and now what we have left is pi r over 2 times dr. Take that pi over 2 out, integrate 0 to r of r dr. That's going to give us pi over 2 times r squared over 2 from 0 to r, which is going to give us pi r squared over 4, which is going to be our final answer. And this is, I believe, our final integral. Not really sure why they added this one in at the end, because it's definitely the easiest. Just the integral of 2x plus 1, power rule question. Integrate them both, you're going to get x squared plus x plus c. So that's all the integrals there. So this next question is just going to be a bunch of derivatives. Important rules to remember are chain rule, product rule, quotient rule. They're a little cut off there, but we'll be using them a lot, so I'm sure you'll get them if you don't already know them, which most of you probably do. So first we're going to be using the product rule here because we have two functions multiplied by each other, cos to the fourth times sine x. The derivative of cos to the fourth of x is going to be 4 cos to the third of x times the derivative of cos x, which is negative sine x, right? And similarly, on the other side, we're going to have the derivative of sine x times cos to the fourth. This is going to give us 4 cos to the third x times negative sine squared of x plus cos to the fifth x, right? Basically what we're doing here is we're just taking the derivative of that first function times the second function plus the derivative of the second function times the first function. There's a trig identity, 2 cos x sine x is equal to sine 2x. Since I had a lot of coses and sines there, it looked a little easier to simplify, right? So we could change this into cos to the fifth of x minus sine of 2x squared times cos of x. So that's about it for this one. This is just a product rule question, right? F of x times g of x goes to f prime of x g of x plus f of x g prime of x. Now this second question is going to be a quotient rule question, I believe. It's going to work with exponentials there. So we have the derivative of a e to the negative bx over cx squared, right? So the quotient rule is going to be that top function, the derivative of that top function times the bottom function minus the derivative of the bottom function times the top function over the bottom function squared, right? And I'm showing in the corner right there how to do the derivatives of e to the anything times x. You just take that the exponent part there, so e to the kx goes to k e to the kx. The integral, though, is the opposite, where you'll do 1 over, right? And just showing that you can't do the integral when x is above 1. Not really related to this problem, but a good thing to know, right? That's actually, I think, called the error. So it gives an error, right? So now we just take the integral of a e to the negative bx. We pull that negative b down. Then we're also taking the derivative of, I said integral there, the derivative of cx squared, which is 2xc, putting that all over cx squared squared. You can leave it in this form if you'd like, but it's always nice to simplify. We see we have a c in every term, an x in every term. We could pull out a negative a e to the negative bx from each term, and that'll give us a simplified answer of negative a e to the negative bx b plus 2 over cx cubed, I believe is what we should get there. Yep, a bx, not just b there, because we had an x squared. Here we go on to the third integral, which is 5x to the fourth. Real easy one. Power rule there. Just pull that 4 in the front, minus 1 from it. 5x to the fourth goes to 20x to the third. The next one, we're going to have the derivative of x times x squared minus 4 to the 1/2. Looks a lot like that integral we did in the last question, but we're definitely going to be doing it in a different way, right? We're going to be doing the chain rule and also the product rule, so it's going to be a double there. So first we're going to be taking the derivative of x, right, which is 1, and we're going to be multiplying it by that function. Yeah, so I'm just writing out there what our f of x and what our g of x is. So the derivative of f of x is just going to be 1 times g of x. and then plus x times the derivative of g of x. So the derivative of this, you're going to pull the 1/2 down. That 1/2 is going to go to a negative 1/2, and then you have to multiply it by the inside of that function, right? So you're going to multiply it by the derivative of x squared minus 4. So you're going to multiply that by 2x, right? So that's what you're going to get there, which is just going to simplify a bit to the square root of x squared minus 4 plus the 1/2 and the 2x. Those constants are going to cancel out, giving us an x squared over the square root of x squared minus 4. So that looks all good there. We're going to move on to the fifth derivative. This is just going to be the derivative of sine x plus cos x plus tan x plus secant x. So this question is not really asking for the derivative of all of these added together. It was asking for them individually, but you might as well turn it into one derivative. So the derivative of sine is cos. The derivative of cos is negative sine. The derivative of tan is secant squared. The derivative of secant is secant plus tan. Sorry, not plus, just the derivative is secant tan. The derivative of cosecant is negative cosecant cotan, and the derivative of cotan is negative cosecant squared. But if you ever forget what these derivatives are, you can always solve for them by just taking the derivative of whatever one you've forgotten, right? So I think we'll go ahead and do that for cotangent squared. So let's say you forgot the derivative of cotangent is negative cosecant squared. Cotangent is the same thing as cosine over sine. So you could just take the derivative of cosine over sine, and that will give you negative cosecant squared, right? So let's derive that. Yep, so if you don't remember exactly why cotangent is equal to cosine over sine, cotangent is 1 over tan x, right? Tan x is sine over cos, so it's 1 over sine over cos. Pop that cos to the top, and you have the derivative of cos over sine, right? And that should just be recognized as a quotient rule question, right? So we're going to be taking the derivative of cos times sine minus the derivative of sine times cos over sine squared, right? If you want to look at the chain rule there, you could see it for a couple seconds, right? Yep, so we're going to be doing the quotient rule. So it's going to turn into negative sine times sine minus cos times cos, right? Over sine squared, right? Because that's our g of x. So that can easily be simplified into negative sine squared plus cos squared, right? That's the trick if you're not recognizing it. Sine squared plus cos squared is 1, right? That's a very famous trig identity. So you're just going to be left with negative 1 over sine squared, which is going to give you negative cosecant squared, right? Because cosecant is 1 over 5. And so that's going to be our answer. So in case you forget it, you could do the same thing for any of those trig functions in case you forget, you know, secant, cosecant, cotan. If you ever forget those little less common ones, that's how you do it. So the derivative of ln x is 1 over x, right? The integral of 1 over x is ln x, and the derivative of 10 to the x is going to be 10 to the x times ln x. Ln 10. Just by definition there, that's how you do derivatives like that. So now we'll move on to g, which is the derivative of x plus x cubed plus sine x cos x plus sine of x. Yep, just sine of x. Derivative of x is 1. Derivative of x cubed is 3x squared. Sine x cos x is equal to 1/2 sine of 2x. So you can do this from the product rule, or you could just do this from that trig identity. I chose to do it from the trig identity because it's a little bit less work, right? You just wind up getting cos of 2x. If you do the product rule, you'll get two separate expressions added together, right? So we'll do that right now. So we get the derivative of sine x times cos x is going to be equal to cos squared of x, right? minus sine squared of x, because the derivative of cos is negative sine, the derivative of sine is positive cos, and this is equal to cos 2x, which is a trig identity, right? But if you don't remember that trig identity, of course, you could always just look at what cos x times cos x and what sine x times sine x equals. So cos squared of x is 1/2 plus cos of 2x. Sine squared of x is equal to 1/2 minus cos of 2x. We, over 2, right? We looked at this in an earlier question. So that's going to go to cos of 2x, right? Because 1/2 minus 1/2 is 0, and cos of 2x plus cos of 2x, both of those are over 2. It's just going to give us cos of 2x, right? So this isn't really doing the derivative there. Any of these methods should work, right? These are just different trig identities to get to the same place, right? So definitely cos of 2x there. And then, of course, the derivative of sine is just cos, right? So that is this one. The next derivative we'll be looking at is just x to the 5th plus cos x, e to the x plus sine of x squared over 3. Derivative of x to the 5th is just going to be 5x to the 4th. For e to the x cos x, we're going to be using the power rule. And for sine x squared over 3, we're going to be using the chain rule there, right? Because we don't just have x in the middle. So when we take the derivative of sine of x, it's going to give us something. It's just going to give us cos x, but if we take the derivative of sine of something inside, we're going to have to multiply by the derivative of that inside aspect, right? So this is going to go, from the product rule, we have the derivative of cos, which is negative sine times e to the x, plus cos times the derivative of e to the x, which is e to the x, and then we're going to have the derivative of sine x squared over 3, which is cos x squared over 3 times the derivative of x squared over 3, which is 2x, right? So that's our answer there. Looks like we're moving on to I, which is x to the 1/2 plus x squared sine squared of x. X to the 1/2 is going to go to x to the 1/2 minus 1 times 1/2, which is going to be 1/2 rad x. The derivative of x squared is 2x, so that's going to give us 2x sine squared of x, and then the derivative of sine squared of x is 2 times sine x times the derivative of sine x, which is cos x, and we've gone over this a bunch of times, that 2 sine x cos x is equal to sine 2x, so this is all going to come out to 1 over 2 root x plus 2x sine squared x plus x squared sine 2x. So this next question is just asking about what integrals are, really, and then the question after that's asking about derivatives. I'm not going to try and go over what integrals and derivatives are. There's a whole lot to both of them, and so I just thought I'd give a couple of important aspects of both. We'll be using integrals and derivatives the entire time, so these differences are definitely important to know and understand. So this question is asking us to prove that 2x is the derivative of x squared. You can't just use the power rule here and say, here you go, I proved it. In the last slide, we had the definition of a derivative written down. And so if we plug in x squared into the definition of a derivative, we're going to say that the derivative of x squared is equal to the limit as h approaches 0 of x plus h squared minus x squared. So that's f of x plus h minus f of x all over h, right? And so you can't just plug in 0 here, right? Because that obviously gives us something over 0, which isn't cool, but luckily for us, x squared and negative x squared cancel out, giving us an h in every term. Otherwise, we always could use L'Hopital's rule if it really was over h and there was no canceling, but we have h's in every term, so this will give us h plus 2x, plug in 0 for h, giving us 2x, so we proved it. Good job. So this next question here is a limit question, and we're going to have the limit of sine x over x as x approaches 0. And the tricky part of this limit is just that you can't plug in 0, right? Because we have a 0 over 0. There's no factoring to be done either. So we're going to have to use L'Hopital's rule. So that rule just states that if you have the limit as x approaches 0 of f of x over some x where you can't plug it in, that's equal to the limit of taking the derivative of the f of x, the derivative of the bottom there, taking the derivative of all those independent parts of the limit, and that'll be the same. Right, so we can then take the derivative of sine of x, right? The derivative of sine of x, which will give us cos of x, and we could take the derivative of x, which will give us 1, right? So that's the basic idea. Then once we plug in 0 into cos of x, we're going to just get 1 over 1, right? So that's how you do this one. So this next question here is just asking you if you know how to do integration by parts, the chain rule, and the quotient rule. So I wrote those rules up there. Not that much to talk about here. There's no actual problem to be solved. I think most of you guys will know how to use these rules pretty comfortably, especially since we just went over a bunch of integrals and derivatives. So yeah, nothing too crazy about this one. Okay, so now we're going to do some graphing questions. Important things to remember when graphing is that our first derivative is going to give us our max and min. Second derivative is going to give us our inflection points. Our first derivative is where you can get some zeros of the function, and that it's always important to remember and see if you just notice anything unique or obvious about the function that would make it easy to graph, or something that's important not to miss. So our first function is e to the negative x squared. Our derivative is negative 2x e to the negative x squared. When is this equal to 0? Well, we could see by inspection just that when x is equal to 0, right? So we could tell that this is a max. We're going to have a max at 0, 1. If you put 0 into e to the negative x squared, you're going to get e to the 0, which is 1. Right, so our second derivative is going to be negative 2 e to the negative x squared plus 4x squared, e to the negative x squared, by the product rule, right? So we're going to have to figure out when this is equal to 0. That's going to give us the inflection points of our function. So we could see that the inflection points of our function are going to be plus or minus root 1/2, right? So we're going to do our little number line there, and since 0 is between negative and positive root 1/2, that's always an easy one to check, especially when you got these e to the x's and stuff. So that's going to be negative. We're going to have positives on the other sides, and so we know that we're concave down in between our two inflection points and concave up elsewhere. One final thing to note is that e to the negative x squared is always going to be a positive number, right? So we're never going to be crossing over to the 0 axis. That's why there are no zeros of this function, because 1 over e to the anything, if you make that number really, really negative, first of all, it's squared, so it's going to be positive anyway. It's just going to be approaching 0 as you get higher and higher, right, because of that square. So it's also going to be symmetrical on both sides. And so we're going to draw the function. This would be what it would look like if it was concave up in the middle, but we don't have concave up in the middle. We have concave down, right? So this is going to illustrate the difference. We're going to have the inflection points at those two inflection points. We're going to change concavity. Next up, we have the function y equals a sine of x bounded from 0 to 2 pi, but we don't know exactly what that a means. It's not very clear. A could be the arcsine, a could be a constant, so let's just look at both to be safe, right? So let's first take it as arcsine. So y is equal to arcsine of x, right? So first thing we're going to need to do is take the derivative of arcsine of x, which is 1 over the square root of 1 minus x squared. Now, the question doesn't ask us to go into what all the different arcsine derivatives are. It probably doesn't even ask us to do arcsines at all, but I think it's worthwhile. So the derivative of cosine, the inverse cosine function, is the negative derivative of the inverse sine function. The derivative of the secant inverse function is 1 over the absolute value sine of x minus 1, and the derivative of the cosecant inverse function is going to be the negative version of that. But now that I'm actually looking at it for a second time, I think I wrote down the inverse secant derivative incorrectly. It should be 1 over the absolute value of x times the square root of x squared minus 1. So it's positive, and there's an x squared in that square root there. And the cosecant inverse derivative is the negative version of that, so that's still correct. But gotta make sure we get those derivatives correct. I hadn't reviewed those recently. So the second derivative of our function here is going to be the derivative of 1 minus x squared to the negative 1/2, right? It's much easier to do the derivative when you write it that way. And that's going to be pull the negative 1/2 down, make that negative 1/2 a negative 3/2, and multiply by the derivative of the inside of our function. We got two negatives there, and we got 2's on a top and a bottom, so we can cancel all that stuff out, and we have x over 1 minus x squared to the 3/2, which is the same as writing 1 minus x squared times the square root of 1 minus x squared. Now, once again, we could see that x cannot equal 1. X cannot be greater than 1, right? Because that's going to give us, again, a negative in our square root. So we also know that we have an inflection point at x equals 0, right? Because 0 over all that nonsense is going to give us 0. And I think we're just about ready to write down our function once we figure out the concavity here. So when x is greater than 0, you could plug in a 1/2, right? You're going to get a positive value. And of course, if we were to plug in a negative number, we'd still get a positive on the bottom, but we'd have a negative on the top, giving us negative concavity when we are less than 0. So we're ready to draw our function. Remember that the arc sine function is 0 at 0, so that's we go through the origin there. We know that we can't go past 1 or negative 1, because if you plug in negative 1 also into the square root, you're going to get a 0 coming out, right? As illustrated there. So that's a good way of drawing our function. We are bounded by 0 and 2 pi, but you might as well draw it all the way out, right? Since we have that information. So it was just a function that was concave up. It was just a concave up slope from 0 to 1, and there was nothing between 0 and 2 pi. So now we'll look at the function as if a is a constant, right? A could be 2, 4, whatever. We know from experience this is just going to be a sine graph with a amplitude of a, but we might as well go through the process as if we didn't know that, right? So sine of x is equal to 0, not at x over 4, not at x equals pi over 4 and 3 pi over 4, but actually, I'm sure I'll quickly change that to 0 and pi, right? Our sine function is equal to 0 and at pi, and our cosine function is equal to 0 when we are at pi over 2 and 3 pi over 2. So we know we're going to have maxes and mins at pi over 2 and 3 pi over 2. We know we're going to have zeros at 0 and pi. Looking at the second derivative of the function, we also know that those is good. That will be when our inflection points are, right? Because if sine is 0 at 0 and pi, we are going to have inflection points there as well. So if we plug in numbers around our critical points, we're going to get a maximum at pi over 2 and a minimum at 3 pi over 2. And now I think we're about ready to draw the function. However, it's important to realize that when we plug in pi over 2 and 3 pi over 2 into our function, we're going to come out with a and negative a. So after we understand that, we'll just get a sine function that has an amplitude of a. So I'll just let that run out. Next up, we have a very tricky graphing question, so hold on to your hats. We have f of x equal to e to the pi over 2. Maybe e pi over 2, it's a bit hard to read it, but regardless, we have the classic line. So some of you might not be familiar with lines, but they're just these sort of straight functions, and this one doesn't even have a slope. It has a slope of 0, right? So we're going to have a graph that looks like a line through the point e to the pi over 2. I think this question was really checking if you just freak out if they made a constant e and pi. So but I think most of you probably got that one there. We're going to move on to the next function, which is 3x squared minus 17x minus 10. We can recognize this as a classic parabola, but let's figure out exactly where our minimum point is, right? And we know it will be a min because we have a positive x squared, right? It would be a max if it was a negative x squared. So we have 17 over 6. If we plug in a 0, we're going to get a negative number. If we plug in a big number, we're going to get a positive number. So we know we have a min at 17 over 6. Now we're going to take the second derivative, which is just a positive constant, so we know that we're always concave up, which a parabola should be, right? If we wanted to find the zeros of this function, we should use the quadratic equation, which is going to be 17 plus or minus the square root of 17 squared minus 4 times 3 times negative 10. And that's all going to be over 6, right? So I'm not going to bother multiplying out what that square root term is. I'll just call it c, right? And so we know that our graph is going to have a minimum at 17 over 6, a y-intercept at negative 10, and we also know that we're going to have our two zeros at 17 plus and minus c over 6. So that's what our parabola function should look like. So our next function here is going to be x cubed minus x squared, right? So we're going to go through all the same steps that we've been doing. First, we could find where those zeros are. Obviously, 0 minus 0 is going to give us 0, and we also know that 1 minus 1 is going to equal 0, right? So we could plug in those zeros. Next step, we're going to need to find the derivative of this function, set that equal to 0, and then of course we'll be finding the second derivative of this function and setting that equal to 0. That's going to give us our critical points, our inflection points. Same thing as the last four, except for that constant one. And so we have our derivative of 3x squared minus 2x equals 0. X is going to equal 0, and x is going to equal 2/3. That is going to give us our two critical points. And we'll just plug in numbers on each side of them to figure out if those are maxes or mins. I don't think there's that much to say about this one, so I'll just let the work run itself out. Yep, so this is about what our graph's going to look like. We got our zeros in there. We have a inflection point at 1/3, right? It's changing from concave down to concave up. And we have our min at 2/3 and our max at 0, right? And those are both local mins and max. We could see from this function being concave down for the rest of the time, concave up for the rest of the time. It's going to go all the way down to negative infinity and all the way up to positive infinity at the extremes. So this next function here is a bit of a tricky one, definitely a little harder to take the derivatives of, but we're still going to go through the exact same process, right? So we have f of x equals x squared e to the negative x squared. First thing we could realize is that at x equals 0, we have a 0 of our function. In fact, the only 0 of our function, because as we went over before, e to the negative x squared is always going to be a positive number. So we have our point 0, 0 at the origin for this function. Next thing we're going to do is take the derivative by the product rule, right? So we're going to get 2x e to the negative x squared plus x squared times the derivative of e to the negative x squared, which is negative 2x, giving us negative 2x cubed e to the negative x squared. So we're going to be solving this for when it equals 0. We could pull out those e to the negative x squares. We could also pull out a 2 if we want, but that's not necessary, giving us 2x minus 2x cubed equal to 0, right? We could tell that this is going to be 0 at 0 and at 1, right? Plus and minus 1, right? So those are going to be our critical points. Those are going to be our maxes and mins. So we set up our little number line, and we find out that 0 is a min, and both negative 1 and 1 are maximums. So what is our function at 1 and negative 1? Well, it's going to be exactly the same due to the square terms there. So x squared of negative 1 and 1 is both going to be 1. E to the negative 1 and 1 squared is going to be e to the negative 1. So our function at negative 1 and 1 is both going to be e to the negative 1, or 1 over e. So that's going to be our y coordinate at negative 1 and 1. So now we have our two maximums, we have our minimum. Next thing is to find the inflection points of the function, which is definitely the trickiest part of this question. And don't mind those double dots there. Those are lines at the bottom, right? The points are at a y coordinate of 1 over e. So next we're going to take the second derivative. Same thing, but the product rule again, right? Just twice. We're going to get e to the negative x squared pulled out, and a 2 minus 4x squared minus 6x squared plus 4x to the fourth. We could again pull out a 2, but it's not really necessary. Now at this point, I wouldn't expect anyone to really get you to solve the equation 2 minus 10x squared plus 4x to the fourth. Looking at it, I don't see a quick way to solve the question. I think just generally getting it at the extremes would be good enough here. So we could tell that at infinity, at negative infinity, we're going to have concave up there. It looks like we're probably going to have some sort of concave downward. The actual inflection point of the function, if you use a calculator, is at plus minus 0.467 and 0.177. X is 0.467 plus or minus, y is 0.177, and the other inflection point is at 1.51 and 0.233 plus or minus 1.51 plus or minus 0.467. I don't think anyone expects you to actually solve this equation here. You could. It's definitely possible. Definitely not recommended. I think just getting the general shape of the function is worthwhile, recognizing that there probably are solutions to the function and that there probably are inflection points somewhere. Getting a general feel for it is, I think, what they're just asking here. You just got to have it concave up at the end. You got to have those maxes and those mins, and I think that this is how you should go about solving the problem. Right? So I think this is all you got to do here. Definitely a tricky one. The inflection points, I'm not sure exactly what they were going for there, but I think getting to that 2 minus 10x squared plus 4x to the fourth should definitely be good enough, and then drawing in something that looks like the function above. So our next question here is another graphing question. Not sure exactly why this wasn't just part G of question 27, but let's get to it. So we have y equals 1 plus e to the negative x. We know that e to the negative x is equal to 1 over e to the x, which is never less than 0. It's never equal to 0, right? If we plug in 0, we're going to get a y equal to 2, so we know that is going to be our y-intercept there. If we take the derivative of this function, we get negative e to the negative x, right? Derivative of 1 is 0, derivative of e to the negative x is negative e to the negative x. But this is never equal to 0, right? Because this is just negative 1 over e to the negative x. We have no critical points, right? If we take the second derivative of the function, we're just going to get e to the negative x. And so once again, we have no inflection points either, because this is never equal to 0, right? This never changes signs. E to the negative x is always greater than 0. And since we know it's always greater than 0, we actually know that this function is always concave up. Now, the only thing left to do is figure out exactly what is happening to the function, right? Because we know it's concave up, but a concave up function that passes through 0 and 2 can look really different. There's many different ways that can be oriented. So let's look at it as it approaches infinity and negative infinity. So as x is approaching infinity, 1 over e to the infinity is effectively 0. So we could say that y is approaching 1, right? The limit is approaching 1. And so as x approaches negative infinity, we can say that it is approaching infinity, right? Because 1 plus e to the infinity is effectively infinity, right? So we know that as we go more and more negative, the function gets huger and huger, and as we go more and more positive, we get closer to 1. So that's how we graph this function. So this next question is basically asking you what we just did in question 27 and 28. It asks specifically for a parabola, so you could just do a trial where you choose any random parabolic function, try and graph it, then put it into Desmos. But we did this already in a different question, so I just left a couple of basic information about that here. But I think we've all got this if we just did 27 and 28. So this next one's a pretty fun one. We're going to be deriving the surface area of a sphere above water. So the first method is going to come from the equation for a circle, which is y squared plus x squared equals r squared. Y equals the square root of r squared minus x squared. And the way we're going to be doing this is we're going to be rotating it and finding the surface area of the rotated function, which is going to be a sphere in this case, because we're going to be rotating a half circle around the x-axis. And the formula for that surface area function is a to b, the integral from a to b, of 2 pi f of x times the square root of 1 plus f prime of x squared. So we are going to be taking the graph from negative r to r, right, because that will give us a sphere when we rotate it around. And we're just going to be taking it at a positive y, right, because y equals plus or minus the square root of y squared minus x squared, but that function we just drew is the positive, right? If you do the negative part, that's just a circle. We're not going to be rotating that around. So we know r squared minus x squared is our function. What is the derivative of the square root of r squared minus x squared? Well, we're going to bring that 1/2 down. We're going to go r squared minus x squared to the negative 1/2, and we're going to multiply by negative 2x, right? So that's going to give us, should be negative, but it's not going to matter because we're squaring it, negative x over the square root of, added it anyway, negative x over the square root of r squared minus x squared. And when we square that function, we're going to get x squared over r squared minus x squared, right? So now we're going to have to integrate this function to find the surface area of a sphere generally without the water, right? So negative r to r are our bounds of integration, r squared minus x squared, 1 plus x squared over r squared minus x squared, but we're going to try and make that 1 equal to something that we could put in the fraction. So we'll multiply it by r squared minus x squared over r squared minus x squared, so we can actually cancel out those x squares up there. So now we have 2 pi integral still of r squared minus x squared in the square root times the square root of r squared over r squared minus x squared. And we can pull that r squared out. And by pulling out the r squared, we're actually left with the square root of r squared minus x squared times the square root of r squared minus x squared, the inverse, right? And anything times its inverse is just going to be equal to 1, right? Because you're going to have 1/2 minus 1/2 equal to 0. So it's going to be r squared minus x squared to the 0, which is 1. So that really simplifies our function down there. If we had originally tried some crazy u substitution, it might have worked out, but by simplifying what we have in the fractions, it definitely works out very nicely. So now we just have 2 pi r times the integral negative r to r of 1. The integral of 1 dx is just going to be x, so it's x from negative r to r. R minus negative r is going to be 2r, which is going to give us 4 pi r squared, right, which is the surface area of a sphere. So now we're going to jump to method 2 for how to find the surface area of a sphere before we get into the buoyancy aspect of this question. Right, so the second method is a more geometric one where we're going to be integrating the circumference of a sphere all the way up and around, right? So we're going to say that the arc length is equal to r theta. The derivative of that is going to be r d theta, and we're going to be integrating that little ds all the way around. So it's going to be 2 pi r ds, right? That's the circumference that we're working with. And we're going to be doing from 0 to pi over 2 times 2, right? So we'll be doing it twice, right? It's going to be 2 times that half of that ds. So 2 pi r times r d theta, and as we could see, we have 2 different r's there, right? So we're going to have to change one of them. And if we look at how our arc length was set up and how our theta is set up, we can say that that r, that radius, is going to be equal to our big R times cos theta, right? By SOHCAHTOA rules. So we could readjust our integral to 4 pi big R squared, because we could pull out that big R squared because we're integrating in terms of theta, right? Leaving just a cos theta in the integral. Now, we could, of course, guess that that cos theta integral is going to go to 1, right? Because we could already see our surface area formula, but you always have to integrate it out to make sure, right? So the integral of cos theta is sine theta. Sine theta of pi over 2 is going to be 1. Sine theta of 0 is going to be 0, so that is going to give us what we're looking for. So this is a second way of deriving the surface area of the sphere. I prefer the first one because it's formulaic and it's very straightforward, but this also works. You could just get caught up in the weeds a bit. So on to the buoyancy aspect of this question. We're not just trying to derive the surface area of a sphere, we're trying to derive the surface area above water for a sphere. So one way to do this would be through bounds of integration. When you were integrating to find the generic formula, you could have put in bounds so that you would get out a fraction of the generic surface area formula, but I prefer to do it this way, where I know that the formula for a volume above the water is going to be equal to the fraction times the volume of the total volume of the object. So the fraction is equal to the density of the liquid minus the density of the object over the density of the liquid. Since a sphere is perfectly symmetrical, right, and we're assuming that this sphere has uniform density, we can say that the proportion of the volume above the water is the same as the proportion of the surface area of the water. If you just imagine a sphere, it should make some sense, right? And so if, say, our fraction came out to 1/2, we'd know that half of the surface area was above. So our surface area above is going to be density of the water minus the density of our sphere over the density of the water times 4 pi r squared. So I think that's a pretty good way to derive the formula here. So let's get into some differential equations. So the general way that you're going to solve differential equations is you solve for the homogeneous solution when the derivatives equal 0. Then you're going to solve for the non-homogeneous solution, kind of acknowledging the extra funky aspects of whatever specific equation you're working with, and then you're going to add the two. And the way you're going to solve those different equations is by assuming generic formulas or by integrating using differentials. So let's go to the first one, and you'll see a bit what I'm talking about. So we have the second derivative of y plus 6 times the derivative of y plus 9 equals 5. Of course, we could always slide that 9 over to the other side, make this equal to -4, but we're going to be solving for the homogeneous solution anyway. So we're going to be turning that -4 into a 0 and solving. Anytime you have a linear differential equation, it's always worthwhile to assume a e to the rx is your y function, right? So by assuming that, you get the first derivative equal to r a e to the rx, and the second derivative equal to r squared a e to the rx. So you could just plug that into the homogeneous equation, right? You're going to get r squared a e to the rx plus 6r a e to the rx. Your a e to the rx's are always going to cancel out, so you could kind of skip writing them in if you're comfortable, right? And you'll get r squared plus 6r equals 0, r is equal to 0, r is equal to -6. You have your homogeneous aspect of the solution as a e to the 0 plus b e to the -6. That would be your answer if this was the original question, but you have that -4 on the end, so you have to just do some problem solving, a bit of inspection and thinking to think what function would give me -4, right? What function drops that back? So one thing that I always like to think of is let's make y double prime equal to 0, right? And one way to do that is by assuming that y equals ax. Y prime equals a, y double prime equals 0. So you just get 0 plus 6a equals -4, a equals -2/3, and now you're going to have your non-homogeneous aspect of the solution. So this is always going to be the hardest part of the problem, in my opinion, figuring out what that next function is going to be, but assuming ax is good for any constant, right? Now we're going to move on to the second one, which is dn over dt equals -2n, and I'll show you how to do this one kind of the same way as last time and also through integration. So our first method is just assuming that n is a function of t, so dn over dt is equal to n prime. Once again, assume n is a e to the r t this time because rx was more generic. Now clearly it's a function of t, so rt. Then n prime is going to be r times a e to the rt. -2n is -2 a e to the rt. Cancel out those a e to the rt's, you get r equals -2. So n is equal to a e to the -2t. A second way of doing this is by combining the terms, right? Get your n and dn together, get your dt out of there, and then integrate, right? So you could slide the dt over to the other side. You can divide the left side by n, and you'll get 1 over n dn equals -2t. Integrate both sides. You'll get the natural log of n equals t squared, right? -t squared, because it'll be -2. Oh, sorry, that's a dt. Yes, don't forget the d. So it's just -2t, right? You could raise both of those sides from the exponential power. E to the ln n is equal to n, right? E to the ln of whatever is inside is equal to that. And then, of course, you have e to the -2t plus c, right? And so that e to the c is going to be equal to our a, giving us the same answer as last time. Finally, we're going to have y prime equals to xy cubed. This time, you can't just assume a y equals ae to the rx because you got an x there. So you're going to have to change y prime into dy dt. So it's into dy dx, right? So it's very useful to know that, to know both ways of doing it, integration and assumption, right? So we know that it's dy dx because we have it in terms of x, right? Last time it was in terms of t, now we have it in terms of x. dy over dx is equal to xy cubed. We're going to have to get those y terms and those x terms together, and then we're going to be integrating, right? So the integral of 1 over y cubed is negative 1 over 2y squared. The integral of x is going to be x squared over 2, and we're going to have to add a plus c over there as well for the constant of integration, right? We can cancel out those 2's and add a 2 to c, and then we're going to take the negative inverse, which would give us negative 1 over x squared plus 2c, right? Taking the square root of that, we're going to get negative 1 over x squared plus 2c, all that in a square root. But we're not done. Usually we just be done here, but we're actually given x equals 0, y equals 1, so we can solve for our c here. In those last two questions, we just left that a in there, which was just some constant. If we were given conditions, we could find it. Now we're given those conditions. So we know 1 equals 1 over negative 0 squared minus 2c. c must equal negative 1/2, and that will give us a final answer of negative x squared plus 1, right? So that negative 2c turns into a plus 1. So on to the next question, we're just going to be graphing the derivative and the second derivative of this function. So as we can see, we have a very high slope at the beginning, then we have a slope of 0, then we have a low slope. One way of graphing derivatives is just by looking at the slope of the function. On that straight diagonal line, we could tell that has some sort of constant slope. So one way to draw this is that it goes from a high slope to a negative high slope to a constant slope. We also can just realize that that's a parabola there, an upside down parabola, so it's probably going to take the function y equals negative x squared, right? And so the derivative of that would be negative 2x, which looks pretty similar to that slope there, right? Some sort of negative 2ax, right? Because obviously there could be constants in there. There's other terms, but the general shape is about what we got that way. And of course, the second derivative there is going to be just some constant, right? Because now we have a negative constant slope and we have no slope there. So it's going to give us a negative constant and then 0. So this should be the derivative and second derivative of our function. Okay, so on to the next question. One very important thing to realize in this question is that they're not actually telling you to optimize a rectangular fence, right? When I first saw this question, I just optimized a rectangular fence and I just thought I was all good, but then I realized, they just say, what is the maximum area that you can enclose, not what's the maximum rectangular area you can enclose. So first, good idea, just optimize a rectangle. 2 width plus length equals 80. Get a formula for length, plug it into the area equation, right? And you will get 80w minus 2w squared equals 0. Just draw a little graph there. So we know that the slope is equal to 0 at the maximum. So the derivative of our area function is equal to 0 when we're looking for the maximum. Width is 20. Length is 40. We have an area of 800, right? 20 times 40. But we're going to have to check for other shapes, and the best one to go to next is going to be the one that has infinite sides, right? The other extreme compared to a rectangle. Or I guess a triangle would also have maybe even been better than a rectangle to go to extremes, but a rectangle is very reasonable there. We're going to get a circumference equal to 2 pi r over 2 because it's half of a semicircle. We then can get the radius equal to 80 over pi. No optimization necessary here. Just a bit of a problem-solving question. Now we're going to get the area equal to pi r squared over 2 because we have half the area of a circle. Plug in our radius, and we're going to get something bigger than 800. I think it should come out to about 1,020. I think I just estimated to about 1,050, but regardless, it's over 1,000. So we could say that this is probably the maximum area we can enclose. They don't really ask for you to derive the maximum area like that. They just kind of want to see some problem-solving thinking, I think. So next we are going to be optimizing a three-dimensional box that comes from a two-dimensional piece of paper that you kind of cut the corners out and pop open, right? So we're going to have a constant length and a constant width, and we're going to have to figure out what is that X value that's going to give us a maximum volume. It's only five-sided, right? Because the bottom is going to be nothing there. It's just going to be the ground, and let's get to work. So we know that our volume is going to be length times width times height. The height of our box is going to be x, right? The length of our box is going to be L minus 2x because we're going to be pulling out an x from both sides. Our width is going to be width minus 2x, right? And so now we're going to have to optimize this equation. So I think it's a good idea to multiply this out first, right? It'll definitely be easy to take the derivative there. And then we're going to multiply all that by an x on the end. Right, so there's going to be an x on the end of that term. We know that the derivative of this function is going to be equal to 0, and it's in terms of x, right? So LW is going to go LWX, 4x squared is going to go 4x cubed, negative 2xW is going to go negative 2x squared W, negative 2xL is going to go negative 2x squared L, right? We're going to distribute that x out, giving us LW plus 12x squared, right? Minus 4xw minus 4xl, right? So we know that this equals 0, and we're finding things in terms of a generic L and W. So one thing that should immediately pop to mind is, of course, the quadratic formula, right? We could push that W and L together into one term, and now we just have an A, a B, and a C. So x is going to be equal to positive 4 times W plus L, plus or minus the square root of negative 4w minus 4l squared, right? All over 24, right? Yeah, so that 16 is not really that accurate, right? So it's going to be 4 times w plus l squared. It's a little tough to write that in that small space. And that is going to be our answer for the optimal volume of the box. So next up here, we got a pretty basic velocity and distance question, I guess. We just got two guys, each running at 5 miles per hour. They are going to be crashing after 1 hour. And basically, we're just going to be saying that after an hour, fly's going 20 miles an hour. It's gone 20 miles in total. So I think that as long as you recognize that they're going to be crashing after an hour, you should be all good if you remember the relationship between velocity, distance, and time. Next up here, we've got three different mathematical concepts: the Laplace transform, Fourier transforms, and Taylor series. The Laplace transform is going to help us solve differential equations, and it's going to be the integral from 0 to infinity of e to the negative st f of t, f is a function of t times dt. We're going to be solving a Laplace transform later, so we can go into more depth then. A Fourier transform is good for solving differential equations and also analyzing periodic functions. It's great for transforming a function into a function based on frequency, right? So a lot of times you'll see it written as f of omega there. And a Taylor series is a great way of estimating functions as polynomials, and this will be expressed often in series form as shown below. So that's a brief rundown of them. Never a bad idea to go over examples and try them yourself. Laplace transform, I think, is the only one that we'll be doing later on, though, so we can look forward to that. Next up here, we've just got a brief rundown of L'Hopital's rule. It's useful when you are taking the limit of something that is over 0. So you could always just take the derivative of any aspect of your limit, and you could then plug your limit in to figure out what it actually evaluates to. We did this before with the limit of sine of x over x, and you could do this with any limit like that. I don't think we'll be using this again later. Maybe we will, but it's definitely a useful rule to learn and is going to help you solve a lot of limits. Next up here, we've got a basic probability question asking you, what are the odds you roll a 7 with 2 dice? Now, I'm sure there are many ways to do this, but the one I find simplest is just writing down all the possible outcomes and just counting how many of them result in what we're looking for, right? So we want to figure out how many times this is going to add up to 7. So we could just look, well, our first die, we can get a 1 through 6, and then on our second roll, we can get a 1 through 6 again, of course. So let's count how many of those are 7. So in our first die, we have a 1 plus a 6 is a 7. In our second die, a 2 plus a 5 is a 7. Then our 3 plus a 4 plus a 3, a 5 plus a 2, a 6 plus a 1. All other combinations don't result in a 7. So that's 6 out of 36, giving us a 7, giving us a 1 out of 6 probability of rolling a 7 with 2 dice. So this next question here is definitely a pretty tricky one. It's asking you, if a population is doubling after 2 years, how long will it take for it to triple? Now, what you don't want to do is what I'm going through right now, which is that you say that you could set up some sort of chart where you look at when the population is doubling, right? So at t equals 0, let's say you have a population of 2. After 2 years, you have a population of 4. After 4 years, you have a population of 8. Whereas it tripling? Oh, it's tripling at 3 years, right? There should be a 6 right there. But that is not what you want to do. What you want to use is exponential growth functions, right? We've been assuming a lot with our differential equations. We're going to assume again that our population is equal to some AE to the RT, right? Some exponential growth function based on time, right? So, yep, exponential growth function. So what do we want our exponential growth function to equal when we're at time equals 0? Well, we want that to equal whatever our initial population is, right, that we're doubling and tripling. So that's just going to be expressed as P naught, right? So now we know that our exponential growth function is equal to P naught e to the RT. And we know that after 2 years, our exponential growth function is going to equal 2 P naught. So we could say that 2 P naught is equal to P naught e to the 2R, right? Because we know that t is equal to 2, then the function is going to be equal to P naught. Cancel out those P naughts, multiply each side by ln, right? Because then that will cancel out that e there, giving us ln of 2 equal to 2r. R is equal to ln of 2 over 2. Now we actually know exactly what our exponential growth function is, and so we're ready to figure out at what time our exponential growth function is equal to 3p naught, right? Now we have our r, right? So we can figure out what our t is. So 3p naught is going to be equal to p naught times e to the r, which is ln of 2 over 2 times t, right? So we can cancel out our p naughts again, do the same trick with the ln, giving us ln3 equal to ln of 2 over 2 times t. We could pop that 1/2 ln2 to the other side, giving us what our time is, right? So that's definitely a more roundabout way of getting pretty close to 3 anyway, right? But that's actually how you're going to want to go about solving this question. And another property of natural logs and logs in general is that you could pop that constant in the front into the exponent inside your natural log. So this is going to give you a little bit over 3, not exactly 3. So we're going to go about solving this question using exponential growth functions. So this next question is another interesting one. We're given a function, we're given the area under the curve of the function, and we are asked to find what that function originally was. So what do we know about this function? We know that since it's going to 1 in the x direction and the full area is 4a, we know that f of 1 is equal to 4a. What else do we know? If we use g of x as notation for the integral of f of x, we know that the integral from 0 to 1 of that f of x is going to be equal to 1a, because it's the area under the curve, which is going to be equal to g of 1 minus g of 0. We know that g of 0 is 0. We also know that f of 0 is 0, so we know that g of 1 is equal to 1a. So what function has these properties, right? The question is really just asking you to just think and do some problem solving a little bit. I don't think there's some formulaic way of getting here, at least not one that I know of. And basically, we're just going to use inspection at this point to figure out what function equals 4 at x equals 1, right? What function has an integral that's going to equal 1 at 1. And if you just think about it, the only one that came to mind for me was x to the fourth, because its derivative, which is the function we're looking for, is 4x cubed, right? That was the only one that I thought of that gave me a 4, gave me a 1, gave me a 0. So one answer is definitely x to the fourth, and 4x cubed is the actual function. There might be others, but 4x cubed worked pretty well for me. So this next question is a bit physicky, but of course it still involves a lot of mathematics. We're given a circuit here, and we're asked to derive the formula for current as a function of time. So if we use Kirchhoff's loop rule here, or just generally that the voltage of the battery is going to be equal to the voltage drop across the resistor and the capacitor, we know that V minus IR minus Q over C is going to be equal to 0. We also know that that current is equal to the derivative of charge over the derivative of time, so the integral of current is going to be Q. So we could substitute Q as the integral of current. We could take the derivative of both sides. Voltage is going to be a constant. I is a function of time, right? So I is going to go to I prime. The integral of I is going to go to I, right? This is just what we got so far. And so now we can assume once again that I is equal to some AE to the RT, right? And our job is going to be to find that R. So I prime is then going to be RAE to the RT. This expression is, of course, equal to 0, right, from above. And we're going to get that negative R AE to the RT times R is equal to positive I over C, or positive AE to the RT over C. We can cancel out those AE to the RTs, and we'll get that the little r, which is what we're trying to find, right? The big R is equal to the resistance of the circuit, but our little r is equal to negative 1 over RC, and RC is actually equal to tau, which is known as the time constant. So now we know that I as a function of t is equal to AE to the negative t over tau. But from our understanding of circuits, we can actually figure out what that A is, because at time equals 0, our current is actually going to equal the current from the battery, because the capacitor is acting as just a plain wire there. And so our current is actually going to equal I battery e to the negative t over tau, or in terms of what we've gotten from the circuit, I battery is going to equal to the voltage from the battery over R. So we can get a final answer of I as a function of time equal to V over R e to the negative t over tau. So this next question here is asking us to illustrate how to solve differential equations using matrices. And I thought there would be no better way to do that than just doing an example ourselves, right? So obviously this is one way to show that you know how to do it. So we're going to go through a problem. So imagine you have an x1 derivative and an x2 derivative equal to 5x1 minus 3x2 and negative 6x1 plus 2x2. Now we're going to turn that 5x1 minus 3x2 minus 6x1 plus 2x2 into a matrix, right? And we're going to say that that matrix times the vector x1, x2 is going to be equal to those derivatives there, right? This is just another way of writing that equation. And what we're going to do is find the eigenvalues and eigenvectors of that matrix, and that's going to give us what our functions are, right? So first, let's go ahead and find those eigenvalues and eigenvectors of the 5, negative 3, negative 6, 2 matrix. And of course, if you had a more complicated equation, this would just be a bigger matrix. Finding the eigenvalues and eigenvectors would just be a bit harder, but it's the exact same process, right? So we're going to say that our vector x, which is equal to x1 and x2, right, is going to be equal to a times the eigenvector, e to the eigenvalue t, plus b times the other eigenvector, times times e to the second eigenvalue times t, right? And so we're going to go ahead and find our eigenvalues. We're going to do 5 minus lambda and 2 minus lambda in the diagonals, negative 3 and negative 6 on the other diagonal, and we're going to be subtracting AC minus BD, right? So in order to find eigenvalues, we need to find the determinant of the matrix. When the determinant of our matrix equals 0, that's going to give us our eigenvalues. So this is what we're going to get here after we multiply out. We're going to get a lambda squared, a 10, negative 7 lambda, and a minus positive 18 from the other diagonal there. That's going to give us a lambda squared minus 7 lambda minus 8, or lambda minus 8 times lambda plus 1, giving us the eigenvalues of 8 and negative 1. Now, in order to find the eigenvectors, we're going to need to find the null space of our vector at each given eigenvalue, right? So we're going to plug in 8 to lambda, we're going to plug in negative 1 to lambda, we're going to do this process twice, and it's going to give us those vectors, right? So as you can see, I'm plugging in the eigenvalues into that expression there for what our functions are going to be. So first we're going to do lambda equals 8, 5 minus 8 is negative 3, and 2 minus 8 is going to be negative 6, right? So if we add negative 2 of that top row to the second row, we're going to get 0, 0 there. If we divide the top row by negative 3, we're going to get 1, 1. And what this matrix is really saying is that negative 3x1 minus 3x2 equals 0, or negative x1 equals x2. So if x1 equals 1, x2 is going to be equal to negative 1. So that's going to be one eigenvector, and then we're going to do the same exact process, except our lambda is going to equal negative 1. So 5 minus negative 1 is 6, 2 minus negative 1 is 3. So that's going to give us the matrix 6, negative 3, negative 6, 3. Once again, we could just add 1 this time of the top row to the bottom row, giving us 6, negative 3, 0, 0. Now this is saying that 6x1 equals 3x2, or we could divide that by 3 there, giving us 2, negative 1 as our matrix. 2x1 equals x2, so we will get the eigenvector of 1, 2, if we don't want to bother doing the fraction 1/2, 1, right? So those are our null spaces, those are our eigenvectors, and that will be 1, 2. Right? So now all we have to do is that we know that the x vector is equal to x1, x2, right? And that's going to equal what we have there. And so we could just take those top values of our eigenvectors and say that that's equal to x1, take the bottom values of the eigenvectors and say that's equal to x2, right? So 1 times a e to the at plus 1 times b e to the negative t is going to be our x1, and negative 1 times a e to the at plus 2b e to the negative t is going to be our x2. And so that's how we're going to solve those sort of couple differential equations with matrices. Create a matrix from the original equation, find the eigenvalues, find the eigenvectors, and then just reorganize it from the vector there. So this next question is asking you for the sum of n as n goes from 1 to 100. So it's basically saying, without using any sort of a calculator, what is 1 plus 2 plus 3 plus 100, right? All the way up to 100. And the way you really are going to have to wind up thinking about this is that from 1 to 49, you have a pair of numbers that equals 100. 1 plus 99 is 100, 2 plus 98 is 100, 3 plus 97 is 100, 4 plus 96 is 100, all the way up to 49 plus 51 is 100. So we have 49 terms that equal 100, right? But what we also have is 50, right? Because 50 plus 50 equals 100, and there's no pair there, and then we also have an 100 left over. So basically what you have is 49 times 100 plus 50 plus 100 is going to be a way to evaluate this sum without a calculator. This is just a bit of a question making sure you know what sums are, and a question to just see if you could figure that out yourselves. You know, it's not that intuitive, but once you understand the trick, this could really be applied to any sum like this. So it's going to come out to 50-50. So next up, we have a center of mass question. The formula for center of mass is that the center of mass times the total mass is equal to the center of mass of each part times the mass of that given part, right? So we can break this up into two parts here. The bottom part is a 1 by 1 by a cube, and we can say that mass is equal to density times volume, right? And the reason we're going to do that is because we're not given the mass. What we're given is the volume, and those densities are going to cancel out, right? So the center of mass of that first one, if we center it at 0 is between the two blocks, right? The center of mass of this block is going to be negative a over 2. We're assuming uniform density for everything, right? So That's going to come out to rho times negative a over 2 for our center of mass times the volume, which is 1 by 1 by a. And then for the second block, it's very similar, except we have a length of 1 minus a, right? Sorry, a width of 1 minus a instead of just 1, right? So now that we have our center of mass times mass for both of the pieces, we could equate that to the center of mass in total, which is what we're looking for, times the mass total. And we also have the mass total of both pieces, right? Because the mass total is just going to be the mass of the first one plus the mass of the second one. So what's the mass of the first one? The mass of the first one is the rho, right? We're going to have density in both of them times the volume of the first one plus the volume of the second one. The volume of the first one is just A. The volume of the second one is 1 times 1 minus A times A, right? Which is going to come out to A minus A squared, right? Yep, so that's what we got there. And we're going to equate that to the center of mass of each individual part times their masses, right? Which is what we found before. So that's rho times A plus A minus A squared being equal to all that stuff right up there. So we can cancel out the rows because we have a density in every term, and that's going to say that the center of mass is equal to A squared over 2 plus A squared minus A cubed over 2 also. So the reason we have A squared plus A squared minus A cubed comes from what we found in those top two parts, right? Rho A squared over 2, rho A squared minus A cubed over 2, and then we're going to put that all over the total mass, which we just found to be A plus A minus A squared, which is 2A minus A squared. This is all going to give us, right, we have negative A squared because in that first one it was negative because the center of mass was negative. So we can cancel out those A squared, which is going to give us negative A cubed over 4A minus 2A squared. We can cancel out a from each term, giving us a final answer of negative A squared over 4 minus 2A. That's how we do that center of mass question. Next up, we're being asked to classify differential equations. The three important things to note, I think, is whether or not it's homogeneous, which is basically whether or not it equals 0, what order it is, which is going to be the highest derivative you have, and whether or not it is linear, right, if you have a squared term or not. So let's go over those bottom two. What is that? Well, we have a double derivative there, so it's second order. It equals 12, so it is not homogeneous. And we have no squared terms there or any sort of big exponents, so it is linear, right? So we'd be assuming some sort of a e to the rt there. Next up, we have an equation that only has first derivatives, right? Let me just spell homogeneous correctly. So we have an equation that has just first derivatives, so it's first order, it's equal to 0, so it's homogeneous, and we have a cubed term there, so it is non-linear. So we can't just assume something like the ae to the rt this time. We'd have to use break it up, integrals, all sorts of other strategies. Next up, we have a differential equation that is a second order, linear, non-homogeneous differential equation. Second order because we have a double derivative, linear because we have no squared terms, and non-homogeneous because it equals e to the negative t. So first we're going to solve it as if it was homogeneous, right? And then we're going to add that to our non-homogeneous solution. So assume x equals some a e to the rt. That's going to give us r squared times the function plus 5r times the function plus 6 times the function equal to 0, right? Because we're going as if it was homogeneous. So we can cancel out all those a e to the rt's, giving us r squared plus 5r plus 6 equal to 0. Now we could factor that into r plus 3, r plus 2, giving us an r equals to negative 3, r equals to negative 2, letting us know that the first part of our solution, first part of our function is equal to a to the negative 3t plus b e to the negative 2t. And we're using t because it's equal to e to the negative t, right? So it's probably a function dependent on time. Next, we're going to assume that x equals some a e to the negative t, because when we plug that into the function, we're going to get something that is all e to the negative t's, and we'll be able to just solve for that a. That function should work there. That's just some sort of inspection, some intuition, right? There's really no formula for knowing exactly what to plug in. It's all based on the non-homogeneous aspect of your equation, right? So if you assume that x equals some a e to the negative t, x prime is going to be the negative of that, x double prime is just going to go back, right, because times negative again. You're going to get a e to the negative t plus negative 5a to the negative t plus 6a to the negative t equals e to the negative t. Cancel out all those e to the negative t's so that now we can just solve for a. We're going to be left with 2a equals 1, a equals 1/2. Now you have the non-homogeneous aspect of the function, right, e to the negative t over 2. We could just add that on to our homogeneous solution to get the full solution for our differential equation. Next up, we're going to be finding the Laplace transform of t, right? Our f of t is going to be equal to t. So that is going to be the integral of 0 to infinity of e to the negative st f of t, which in this case is going to be t. So our Laplace transform, which sounds a bit big and scary, is just going to be an integral, right? It's just going to be an integration by parts. So we have e to the negative st times t, u is going to be t, du is going to be 1, our dv is going to be e to the negative st, and the integral of that is going to be 1 over negative s, right, times e to the negative st. So now we're going to do integration by parts. U is t, v is negative 1 over s, e to the negative st. So it's going to be negative t over s, e to the negative st, and then from 0 to infinity, right, minus negative 1 over s times e to the negative st, or just plus what's inside the integral. All from 0 to infinity. If we plug infinity into there, we're going to get infinity over s times e to the s times infinity, right? And infinity over an exponential to infinity is going to be, the exponential to the infinity is going to be much bigger, so that's going to go to 0. And of course, 0 over s is also equal to 0, right? So just to clarify, we have an infinity over an infinity, but the infinity at the bottom is much bigger, so you could just make that 0, right? So now we're going to have 1 over s, because s is a constant, right? The integral from 0 to infinity of e to negative st, giving us negative 1 over s squared, e to the negative st from 0 to infinity, e to the infinity. 1 over e to the infinity is going to be 0. 1 over s squared is going to be 1 over s squared, giving us a final answer of 1 over s squared as the Laplace transform of 1 over s squared, not Lagrange, Laplace. Next up, we have another differential equation. It's a second order differential equation, non-homogeneous because it's equal to sine x, and linear. So we're going to assume y equals a e to the rx. In the homogeneous case scenario, giving us r squared plus 4r plus 3. I skipped actually writing in the a e to the rx's because they're all going to cancel out anyway, right? We can just go straight to finding out what our r's are. So y is going to equal a e to the negative 3x plus b e to the negative x. That's going to be our homogeneous solution. But now we have to check for non-homogeneous solutions. And since we have a sine x as the answer, we can assume that our function is sum y equals a sine x plus b cos x. So now we're going to get the derivative and the double derivative, and we're going to plug that into our non-homogeneous equation. So our derivative is a cos x minus b sine x, and our double derivative is going to be negative a sine x minus b cos x. Now we're going to plug that in, right? So we're going to plug negative a sine x minus b cos x into y double prime. We're going to plug in 4 times a cos x minus b sine x into our 4y prime. And we're going to plug in 3 times a sine x plus b cos x into our 3y. And that's all going to equal sine x. And from this, we should figure out what our a term is, what our b term is, and we could plug it into our full equation. All right, so we have a lot of trig terms there. It's all going to be equal to sine x. We know that all the sine terms are going to add up to sine x, and all of the cosine terms are going to add up to 0, right? Because there's no cosine terms on the other side. And we know that there is one sine term on the other side. So negative a sine x minus 4b sine x plus 3a sine x equals sine x, right? We can group all the sine x's together. And we know that negative b cos x plus 4a cos x plus 3b cos x is all going to equal 0 because there is no cos x's, right? So we can cancel out all those sine x's, giving us 2a, right, 3a minus a, minus 4b equal to 1. And we're going to do the same thing for the cos x's, right? We're going to have two equations, two variables, right? And that should definitely be solvable. So we can cancel out the cos x's, giving us 4a plus 2b equals 0, or 2a equals negative b, which we could definitely plug into that top equation, giving us negative 5b equals 1, or b equals negative 1/5. A is equal to negative b over 2, giving us 1/10, and we could just plug that back into the top equation. So y equals a e to the negative 3x plus b e to the negative x plus 1/10 sine x minus 1/5 cos x. That's going to be our full solution. Next up, we have another differential equation, dx over dt is equal to x over k. So we're going to be doing this in two methods, one where we assume and one where we use integration, right? So dx dt is the first derivative of x, and so we're going to have x prime equals x over k, right? So we can go r equals 1 over k, right? Because we can cancel out those a e to the rt's, and so we'll get x equals a e to the t over k, right? Because it's going to be a function in terms of t. Another way to get this is by saying that dx over dt equals x over k, and we are going to integrate. We're going to group the x terms together. We're going to move the dt to the other side, right? So that's going to be 1 over x dx equals 1 over k dt. Integrate both sides, giving us ln x equals t over k. And we can raise both sides to the e, right? We could do e to both sides, and then that will be x equals e to the t over k plus c. We could say that e to the c is a, and e to the t over k plus c is equal to the e to the t over k times e to the c, giving us x equals a e to the t over k, which is what we got before. So good continuity there. We're going to hop into another differential equation now, dy over dx plus ky equals 10. Pretty similar stuff there, but this time we're going to be solving it in a homogeneous way and a non-homogeneous way. So y prime plus ky equals 0. Assume an a e to the rt. We know the derivative is going to be r a e to the rt, or actually we're going to be using x this time, not t, because we're given dy dx. So now we're going to say that r plus k equals 0, r equals negative k, y equals a e to the negative kx. But we have that 10 on the end, so how are we going to take care of that? Well, we want y prime to be equal to 0, so y is just going to be equal to a, right? So we're going to have ka equals 10, a equals 10 over k. Our full solution is going to be y equals a e to the negative kx plus 10 over k. Next question is just asking how you would solve this differential equation. Well, the way that I would solve it is that I would just assume a e to the rx and go from there. It's a homogeneous equation, so we're only going to have to do that once. I'd like to add that a in the middle is supposed to be an a prime. Just copy that down wrong, right? So our derivative is going to be r a e to the rx. Our second derivative is going to be r squared a e to the rx. I decided to use c for constant instead of a this time because our function was a. But it's the exact same thing. We're going to wind up getting r squared times our function plus r times our function plus 1 times our function equals 0. We can cancel out c e to the rx on all terms, giving us r squared plus r plus 1 equals 0. That's going to give us an r using the quadratic formula. As we could see, we're going to get an imaginary r, right? And that exists especially in waves, right? It's pretty common to use imaginary numbers in waves, but you would treat this differential equation as any other. You would just plug in for your r and solve, right? Just because you have an I term there doesn't really make any difference. So you'd get our function a equal to a constant times e to the rx, and so a is going to be equal to c times e to the negative 1 plus the square root of 3 times I over 2 plus another constant which we can call d times e to the negative 1 minus root 3 times I over 2. right? So that would be how we'd go about solving this one. The much more common differential equation that uses I is the harmonic oscillator, right? Standing waves are ae to the I omega t, right? Or ae to the I kx, negative I kx, right? That's pretty common in waves. So if you had the differential equation y double prime plus y prime, I think it's just y, yes, y double prime plus y equals 0, you'd get an r squared plus 1 equals 0, and r would equal I there, right? Because r would be the square root of negative 1. So that's the most common form of this. You would see this a lot in quantum mechanics or waves and oscillations, but this is definitely another instance in which you'd have an imaginary number as part of a solution to a differential equation, right? So that would be how you'd solve this one. Just thought that would be important to add there because it's definitely a much more common example of a similar question. So our last question here in the mathematics section is a differential equation with initial conditions. We know what y naught is, so we're going to be finding the homogeneous solution to the differential equation and then using our initial conditions to find what our constant is, right? So we're going to have a e to the rx minus 3r a e to the rx equals 0, 1 minus 3r equals 0, r equals 1/3, so our solution is going to be y equals a e to the x over 3, but we know y0 is 3, so 3 equals a e to the 0, a equals 3, our solution is y equals 3 e to the x over 3, and that's it. So that's about it for the mathematics sections of the Nupoc study guide. Just like to add quickly that none of these answers or strategies are in any way endorsed by the Navy. This is all coming from me and the many resources that I found independently. I hope it was of help. There aren't that many resources out there for Nupoc. It's a great program, and I hope you guys all do great in your interviews. I think you all will, especially if you watch this video, because it's the best video. It prepares you the best. It has the best answers, and just good luck to everybody. And of course, if you ever meet a submariner named Jack, be sure to ask if he has made a Nupoc study guide video. That'll be all. I'll be seeing you.